But now, if you are comfortable, then you can sit. Hello.
Hello, sir.
Welcome all nodal centers for today's this morning section on this is CAT. I'm today taking CAD/CAM and RPT technology. Okay. Before going to start, just I want to know how many centers have connected today. 3. कौन से हैं मैडम? What are those centers? Just let me know. Only Bikaner. Rest of the colleges are joined. Huh? Okay. Okay. Very good morning to all of you. Today I am here. I am P. Sudhakar Rao, working as an assistant professor in mechanical engineering department at NITTTRCHD, Chandigarh. Today I am delivering topic that is new manufacturing technology. One topic that is CAD/CAM and RPT. So before going to start, just I want to give a brief introduction about the what is ICT. Okay. That is since the course is an ICT, that is new manufacturing technologies course. Just I want to give a brief introduction about what is ICT actually. The definition of ICT is, all you know what is ICT stands for? ICT stands for, that is information and communication technology. Okay, that is shortly known as ICT, and it is defined as a diverse set of technological tools and resources used to communicate and to create and to store and manage the information. Okay. And these technologies include the computers and broadcasting technologies and telephony. With these 3 technologies, we can communicate the information to the other people. And next, another thing is parallel to ICT, we have e-learning also. Nowadays, it is mainly e-learning also we are getting. That is, what is e-learning? E-learning is the use of electronic educational technology in learning and teaching. And conceptually, e-learning is broadly synonymous with instructional technology, that is in ICT, that is instructional and communication technology. It is as good as parallel equal to, that is e-learning. And other technologies including in this e-learning are, that is educational technology, technology enhanced learning, that is shortly called as TEL, computer managed instruction, computer based training, computer assisted instruction, and computer aided instruction. We can develop some CI packages using the computer aided instruction packages. We can develop some softwares. Now, next is, that is internet based training, that is shortly called as IBT, and flexible learning. Including in this ICT and e-learning, we have so many technologies, that is education technology, TEL, CBT, CAI, IBT, all these technologies. And now just to focus on that is definition of e-learning. That is web-based training, online education, virtual education, and virtual learning environment, and m-learning and digital learning. These all comes under into e-learning only. ICT learning, it is online or 8 performance measures of any manufacturing system which are indicative status in the manufacturing world. These are manufacturing lead time, MLT, work in process, machine utilization, throughput, capacity, flexibility, performability, and quality. So online learning, what are the benefits we are having in this online learning, that is through ICT or e-learning? That is, it expands opportunity of education. It is expanding the opportunity of education and expands quality of learning. So you can communicate through anywhere in the center. You can communicate to the concerned person, and increases delivery of learning, and lastly improves efficiency of teaching. And if you see, the ICT was the fastest growing technology nowadays during the last decades. Internet has reached 25% of the world's population, faster than any other innovation. If you see these all parameters here, that is electricity, it is 45 years, telephone 35 years, radio 22 years, and internet took only 10 years to develop this status. And now with this ICT, just I'm telling, so what are the new technologies in the mechanical area? Okay, that is some new manufacturing technologies I am highlighting here. That is One, high-speed machining, that is also latest technology. Non-traditional machining, yesterday we have discussed about EDM and all advanced machining techniques like ECM, EDM, ECDM, and plasma arc welding, plasma machining, and water jet machining, laser machining, all this. It comes under non-traditional machining. And another one new manufacturing technology is friction stir welding, that is FSW shortly. So most of the research is going in welding area on FSW nowadays. And another technology, that is mechatronics. As you know, mechatronics, with the help of mechatronics, we can build up the machines like CNC machines with the help of programmable logical controllers and hydraulic and pneumatic systems, all this. And another technique is reverse engineering. Okay, reverse engineering, CNC technology. And others are CAD/CAM, computer-aided design and computer-aided manufacturing, and RPT, that is rapid prototyping. Here which is highlighted with red color. So now I am discussing about this under the new manufacturing technologies. I am discussing today about the CAD/CAM and RPT. So other new manufacturing technologies are RMS, reconfigurable manufacturing systems, FMS, flexible manufacturing system, cellular manufacturing, group technology, computer-aided process planning, computer-aided quality control. These are all new technologies. Under this, today I'm highlighting the CAD/CAM and rapid prototyping technology today. So now we'll discuss about that is computer-aided design, computer-aided manufacturing, and rapid prototyping. By one, we can discuss about all these things: CAD, CAM, and RPT. And the lecture plan I planned according to this. First, I will give the introduction and applications of CAD, and introduction and applications of CAM. After the design process, we can go for the manufacturing, and then fundamentals of CAD/CAM, modeling techniques and hardware and software in CAD/CAM. What kind of hardware is required to develop a software and to work on the software, and CAD/CAM standards and integration. How do you integrate between the CAD as well as the CAM? So that how you can integrate both the processes. Then introduction and application of RPT. And this is the third segment I'm discussing after CAD and CAM, that is RPT. Introduction and applications of RPT. Implementation of CAD/CAM in RPT. How we are integrating CAD/CAM techniques in RPT, rapid prototyping technology. And advances and future scope in RPT. So what are the advances in RPT? Now first we discuss about just briefly about computer-aided design. So as you know, that is computer-aided design is use of computer systems to assist in creation, modification, analysis, and optimizing of a design. And these computer system include both hardware and software to perform the specialized design functions. If you want to run any software, you have to see the configuration of the system, hardware. And then the CAM is computer-aided manufacturing. It is the use of computer systems to plan, manage, and control the operations of a manufacturing plant through either direct or indirect computer interface with the plant's production resources. We can take all the resources and you can use the resources to develop a product with the help of CAM. The fundamentals of CAD. So why we go for the CAD? So what are the benefits we have CAD? That is to increase the productivity of the designer and to improve the quality of design, to improve the communication between the end user and the communicator, to create a database for manufacturing, and interactive computer graphics is user-oriented system where computer is employed to create, transform, and display data in the form of pictures or symbols. It consists of both hardware as well as the software. Now, if you see the design process, how we are going from starting from the raw material to finished product, how we are involving in these all processes, that we will be discussing. The first, recognition of need. If you want to develop any product, first you have to need. What is the need of the design of the process? What is the need, and why you have to develop this product? That is very important. And after taking the recognition of need, then you have to use which process is used to develop this process from making raw material to the finished product. That is recognition of need. Next, that is definition of problem. We have to define the problem. What is for the recognition, and why we have to go for the design and this one. Next, synthesis. We have to, after defining the problem, we have to go for the synthesis. Synthesis, then analysis and optimization. In analysis optimization, we can see the how we can optimize the parameters for all these processes. If you are not optimizing properly, if you are not analyzing properly, then it will go back to the synthesis. If your synthesis is not proper, then you cannot go further analysis as well as the optimization. Then next, if optimization analysis is okay, then we go for the evaluation. That is, we can evaluate the parameters process. And if your evaluation is also not there, means again you are committing mistake at the synthesis area. If you are not doing synthesis properly, you cannot go for further analysis and optimization. For further, again, you can go for the evaluation. So here, then next, after evaluation, you can present a, that is presentation, means what are the product you develop, you can present in a form. That is. Then applications of computer in design. In design, what are the applications? That is, one is geometric modeling, next engineering analysis, design review, evaluation, and automated drafting. Okay, one by one we discuss briefly about these four applications of the design: geometric modeling, engineering analysis, design review and evaluation, and automated drafting. So here you can see geometric modeling, that is recognition of need, definition of problem, synthesis. All these three areas are covering only with the geometric modeling here. The geometric modeling, which is showing by yellow color. The next, engineering analysis, second parameter. Then the next, that is design review and evaluation. And the last one, automated drafting. So these four, geometric modeling. PPT बताइए. Geometric modeling, engineering analysis, and here that is design review and evaluation, automated drafting. These are four clubbed with the design process. Then it is called as a computer-aided design process. Earlier, with white color, we have only the traditional manufacturing process, traditional design process. And now we discuss about the geometric modeling. It is the main designer constructs the graphical image on the screen of the interactive computer graphics system. The construction includes creation of the geometric entities, modification, and display. And it is storing the data in the form of some respective files. Now, the geometric modeling is, geometric model, we have the two kind of techniques, how we can make a geometric modeling. That is 2D modeling and 3D modeling. Again, in 2D modeling, we have the only 2D, that is wireframe modeling or hidden modeling. And the 3D modeling, we can have wireframe, surface, as well as solid modeling. Wireframe modeling, surface modeling, solid modeling. Then applications of CAM. Applications of, you can just see, that is applications where computer is concerned directly to the manufacturing process to monitor or control the process. We can monitor the process as well as we can control the process using the computer, that is computer monitor and control programs. That is manufacturing support applications, applications where the computer support the production operations indirectly. You can see here that is computer monitoring control, how you can control the monitoring, all this computer and process. This is only the one-way process, computer and process, and the process data is transferring to the only one direction. If it is transferring by the bidirectional, that is computer and process data and control signals. This is called bidirectional. And the applications, manufacturing support applications are numerical control part programming, that is with the help of G codes and M codes, we can develop a part programming, and computer automated process planning, that is highlighted CAPP, computer generated work standards, production scheduling, material requirements planning, shop floor control. Okay, these are the some applications. And now we discuss about the product cycle and CAD/CAM. So here, if you see the product cycle, first the customer needs requirement and what is the availability in the market. What is the need in the market? So the concept has to be developed. So if there is need in the market, if there is need for the customers, we can go for the concept, product concept. Next, design engineering. Then the data, whatever the idea, the concept is there, we can feed it to the design department. Then if the design department says draw, then okay, then we go for the drafting. We can go for the 2D modeling or 3D modeling here. And next, process planning. We can make a process planning for that product development. Next, scheduling. If process planning is okay, then we can go for the scheduling. Matlab how much, if weekly basis or hourly basis or monthly basis, how much production should be there by scheduling. Next, if you make the proper planning of scheduling, we can go for the production. Next, quality control. If product is over, it is ready for the marketing, then we have to go for the quality control. We have to check the dimensions and all these parameters, whether the product is okay or not. We have to see. Then next, if the quality control says the product is not good and not up to the mark, then again it has to go to the production area. Then again it goes to the quality. Then finally, after quality check, the product goes to the customer and for marketing. So this is the traditional design process. Now with the help of computers, how we can make this traditional to the computer, that is computer operational. Okay. Now it is in the computer aided design. Okay. So these two, product concept and design engineering, is clubbed with the computer aided design, where we can use the softwares like CATIA, Ideas, Unigraphics, and ProE, Autodesk, AutoCAD, and SolidWorks, Solid Edge, all these softwares. Next, computer automated drafting and documentation. Okay. Then it is clubbed with the drafting and it is replaced by the computer automated drafting and documentation. Next, and this process planning and production scheduling, everything is replaced by the computer aided process planning. Okay, first CAD, then CADD, then computer aided process planning. Next, computerized scheduling, MRP, that is material requirement planning, shop floor control. So after this, again, computer controlled robots, machines. So nowadays in the production system, we have the robots and all these robots, as well as the computer controlled robots, machines. We have all this for the production. Automated guided vehicles, rail guided vehicles, automated storage retrieval system, flexible manufacturing system. All this comes under the production area. Next, computer aided quality control, where with the help of computer aided, we can check the component. Like we have the computer, that is CMM, coordinate measuring machines. That is, with the help of these coordinate measuring machines, we can get the cloud points of the component and we can define the geometry of the particular component. Then now we can see this. Oh, here this is the white color shows the traditional CAD/CAM system, and it is replaced by the computer aided design and computer aided manufacturing with the yellow color outline. So this is about the traditional CAD/CAM and computerized CAD/CAM. Then CAM automation. So here automation achievements are computer numerical control, and that is direct numerical control, computer numerical control. Then machine vision we have, and robots for arc welding, part handling, material handling, all this. Computer integrated manufacturing system, it is shortly called as SIM, and numerical control and computer numerical control. So these are the some automation achievements in the CAM area. Like Mechaton is also one of the one achievement in this automation. And we can see this now, the design tools. What are the design tools and CAD tools here? The hardware, computer, and software. So design tools here, computer, what kind of hardware is required to run the software, and what is the configuration required for this. Okay. Computer graphic concept, then design tools, CAD tools, geometry modeling. If you say this is the integration of all these three circles, that is CAD tools. It is coming all over the thing, that is geometric modeling and computer graphics concepts, design tools. So this is the definition of CAD tool. And if you see about the CAM, so again it is the integration of CAM tools here. CAM, it is the integration of CAD, networking concepts, and manufacturing tools. So what kind of processes do you require for the computer-aided manufacturing? If you integrate this CAD as well, CAM, so this is the integration of CAD-CAM tool, and manufacturing tools are, design tools are there, manufacturing tools are there, networking concepts are there, geometric modeling, computer graphic concepts. All together it is called as a computer-aided design and computer-aided manufacturing tool. And the hardware required, if you see the hardware, that is normally, that is the Intel hardware, AMD, Athlon, Motorola. So this is all the CISC based, CISC based, and RISC based, that is Sunspace, DEC Alpha, IBM Power. These are some hardware. Then output devices, storage devices. And the software required is, that is first of all the operating system, whether it is Windows based, you have to see whether it is performing on the Windows based or the Unix based and its variants. And the application software include, that is what are the other software applications, that is SolidWorks, IDEAS. This IDEA stands for Integrated Design Engineering Analysis Specification. Similarly, the CATIA stands for Computer Aided Three-Dimensional Integrated Application. Computer Aided Three-Dimensional Integrated Application. Then Unigraphics, Pro Engineer, now it is Pro E Creo, and MicroStation, CAD Key, 3D Studio. So these are some applications in the CAD software. So altogether, the main application softwares are AutoCAD, SolidWorks, IDEAS, CATIA, Unigraphics, Pro E, MicroStation, CAD Key, 3D Studio, all these things. Now some CAD standards are there. So to convert from one software to another software data, so the CAD standards are also there. So the main for compatibility, portability, for proper interfacing at various levels, we go for this is GKS, Graphical Kernel System, GKS system, and PHIGS, Programmer's Hierarchical Interface for Graphics, and Core, similarly GKS 3D, IGS. So among all these things, so many graphic standards, the main standards are GKS, that is Graphical Kernel System, then IGS, Initial Graphics Exchange Specification, and STEP standard, that is Standard for Exchange of Product Model Data. Now various standards in graphic programming is, if you go for the graphics database, we have the DXF, IGS, STEP standards. If you go for the application-oriented program, we have the GKS system, GKS standard, and PHIGS and Core. If you go for the graphics function, we have the VDA, VDM. Similarly, device driver, we can have the various standards. Okay, now we can discuss justly about the 2D geometric modeling of a box. How you can design a 2D geometric modeling of a simple box. Okay, so this is wireframe modeling. Okay, only the outer edges are covered. That is called wireframe modeling, and it is the simplest geometric model, and sometimes referred as a skeleton figure, and consists of points, lines, arc, and circle. With the help of the commands points, lines, arcs, and circles, we can develop a wireframe modeling. Geometric modeling of a box. With this is about the surface modeling. You can see this. Only the surfaces are coming. With the help of surfaces, we can develop a box. So this is called surface model, and the more complete and less ambiguous, and edges are spanned by the mathematically defined areas used in shape design, representation of complex objects like car, shape, ships, and rollers. So since the surface modeling is very popular, so that's why we are having so many variants in the automobile cars. If you are going for the particularly Maruti, we have so many variants in particular one car. If you go for the Hyundai Corporation, we have different variants. Because of the surface modeling, we can generate easily surface models. And finally, that is geometric modeling of a box, that is solid model. This is called about the 3D modeling. For this modeling, we can use the softwares like ProE, CATIA, IDEA, Sonigraphic, all these softwares. And the main advantage of solid modeling is that is the least abstract and more realistic modeling, and extremely used in design and manufacturing. Now more popular. Now it is a more popular method, and varied solid modeling techniques are coming up. Okay. So we have that is various solid modeling techniques, that is constructive solid geometry. So here it is shortly called as CSG or CREP, that is constructive representation. Okay. Solid model is built out of solid graphics primitives like basic shapes, joint in a certain order. And if you go for the BREP, that is called boundary representation. Okay. CREP stands for the constructive representation, and B stands for boundary representation. Boundary of surface, that is edges are used to define a surface, and surface elements are assembled to form an airtight boundary, thus making a solid model. This is about the geometric modeling. Now we are going for the second one, that is engineering analysis. So here the analysis of the product is done, analysis of the product, calculation of mass properties, as well as the mechanical properties like Poisson's ratio, Young's modulus, all these things. And then next is finite element method and finite value method. To analyze any of the component, we can go for the finite element analysis. Under this, we have the two techniques. One is finite element method and finite value method. And under this, we can go for the, depending on the component design, we can go various analysis techniques, that is stress analysis, thermal analysis, dynamic analysis, and couple field analysis, and CFD. CFD stands for, that is computational fluid dynamics. It is related to the fluid dynamics. Okay, fluid dynamics, that is hydrodynamics. And the third part is, that is design review and evaluation. Here that we can see the tolerance analysis, how much maximum tolerances we can achieve when we are designing the component. So maximum tolerance, how much we are achieving, and what is the error percentage. Okay. Then interface checking in assembly, kinematic analysis, motion study. So these all includes about the tolerance analysis, interface checking, kinematic analysis. How much maximum we can achieve the tolerances. Then the lastly, that is fourth one, that is automated drafting. So here, creation of a hard copy engineering drawings directly from the CAD database. Whatever the data we generating through the CAD software, we have to put in a storage form. So dimensioning, generation of raw hatched areas, scaling, drawing, all this can be done. Earlier, we used to do with the help of mini drafter. With the help of mini drafter, we are drawing the drawings, and we are saving the files. Now here, dimensioning, generation of cross-hatched areas, scaling, all things can be done by the software itself. Automated drafting. Development of sectional views, enlarged views, like we can go for the isometric views, orthogonal views, orthographic views. Okay, then development of orthographic views. This is the one advantage in automated drafting. Now we can just go for the benefits of CAD. So the main benefit in the why we are going every technique for the CAD means, that is improved engineering productivity. The 100% improved productivity is there. Then shorter lead time. In a shorter lead time, we can develop a product. Then customer modification are easier to make. Whenever the customer says the modification in the product, we can immediately open particular data file and we can modify the dimensions. We can further go for the designing and as well as the manufacturing. So this is the one best technique we have in the CAD. Earlier in the manual drawing, we don't have that much time to modify the designs. And improved accuracy of design here. So accuracy is good and 0% error in the product, and the allowances also maximum reachable. Fewer errors in design and manufacturing, and better inspection of complicated parts, and reduced prototype testing. So these are the some benefits. Now, now I'm highlighting about the computer-aided manufacturing. So far we discussed about the computer-aided design. Now I'm discussing about computer-aided manufacturing. So here that is it is comprises of all the computer-aided manufacturing. So it is NC and CNC machines. It is a manufacturing technology comprises of NC and CNC machines, robotics, and of course the software. With the help of software only we can generate a codes, that is G codes as well M codes to run a machine. And virtual manufacturing is there. Virtually we can see how much part is being removed, how much part is machined. And online inspection is also there. We can, through CMM, that is coordinate measuring machine, online inspection, we check the geometry of the parameters. And CNC with RPT machine, this is also one latest technology. To RPT machines, we are adding the CNC technology so that we can develop a prototype modeling. So earlier we were using only the RPT machine to develop a prototype, and we are taking the additional technology of the CNC to make a RPT products. And CNC with reverse engineering, this is also one new concept. For making reverse engineering process, we are using the CNC. Whatever the master this reverse engineering copied product we can design, and through CNC machine we can machine that particular component and go for the manufacturing. And then normally the terms used in the CNC technology CAM are, that is numerical control. NC stands for numerical control. CNC is computer numerical control. And the DNC is direct distributed numerical control. FMC, that is flexible manufacturing cell. FMEC stands for flexible manufacturing system. Like similarly, we have the SIM, computer integrated manufacturing, CAPP, CAQC, and RPT, that is rapid prototyping. After completion of this CAM, I'm just discussing about the rapid prototyping. Okay. So these are the normal terms being used in the CAD technology. Okay. Now we discuss what is NC machines and CNC machines. What is the difference between NC machine and CNC machines? NC machines it is a programmable automation in which the machine process is controlled by numbers, letters, and symbol. Okay. And here NC machines, we have the paper tape form, and that is MCU, machine control unit, which transfers the data for paper type into the control codes. Okay, that is CNC machine. Either it may be the milling machine or turning machine. CNC machines are here we have the with computer and the controller system, that is machine control unit MCU, and the data is feeding to the CNC machines. And here direct numerical control, that is host computer. So we can see that through distributed numerical control, we can transfer the data to the various systems. Like we have here 4 CNC machines, the same data is transferred to the various CNC machines. Similarly, distributed numerical control, the host computer, we can transfer the data to the simultaneous CNC machines. And you can see that is CNC machining centers. So CNC machining centers are a kind of CNC machine that can perform drilling, boring, milling, tapping, all the processes like drilling, boring, milling, tapping. That's why it is called as a machining center, where we can perform various number of operations. And it is multi-axis control. It may be the 3-axis machining or it may be the 5-axis machining. Okay, tool magazine, and it is containing the various tool magazine containing variety of tools to perform various machining operation, which replaces several conventional processes. If you want to go only for drilling, we can go only with the conventional drilling machine, conventional boring machine. So all the processes are all the processes are clubbed into this tool magazine. If you can see here, this is a tool magazine. We can put which kind of tool material here, tools. And in this methods of CNC program generation, we have 2 kind of programmings. One is manual part programming. Under this, we have the conventional part programming and APT program. That is, APT stands for advanced programming tool program. That is conventional programming. This one. The second one we have the major, that is computer aided part programming. Computer aided part programming. That is solid modeling, toolpath generation. Here it is the sequence steps I am highlighting here. First, we have to make a model, solid model. Then you have to give the machining parameters for the concerned product. Then it will give the toolpath generation. We can go for the post processing so that we can generate a G codes, M codes from the computer system, and verification. Verification stands for here numerical control verification. We can see in the workpiece material how much material is being removed. It is called numerical control check and numerical control verification. And here we can go for the axis here. If you go for the 3 axis, we have the only 3 linear axis, that is X, Y, Z, 3 linear axis. And if you go for the 5 axis machining, we have another 2 rotational axis, that is A and B. Rotation along A axis. A stands for A axis here. It is rotation along the X axis. And B, it is another the 5th axis, which is rotation along the Y. So normally the Z is your tool movement here, X, Y, Z. So now computer-aided manufacturing, we can go for this steps. First, how we are generating the product through computer-aided manufacturing softwares. First, you have to design a model. First, you have to design a CAD model, then a manufacturing model, then that is workpiece model here. That is tool definition. We have to give the tool definition. For if you are going for the drilling, boring, all this, depending on the process, we have to go for the tool definition. If you want to go for the milling machine, you have to take a milling tool. If you want to go for the drilling, you have to take the drilling tool. And here the cutting this is raw material definition. मैडम ये माउस खराब है थोड़ा सा, तो दूसरा देखिए कोई. हाँ ये पेपर है ना, माउस दूसरा देखने से थोड़ा सा ये थोड़ा ठीक से पॉइंटिंग नहीं हो रहा. खराब है शायद इधर.
Hello.
Hello.
This is from JCRC Jaipur.
अच्छा, Jaipur?
Yes, sir. JCRC.
Okay. You are connected, na?
Yes, sir. We are connected.
Okay. So just some interruption is there in this here, some problem. So I'll be continuing the computer-aided manufacturing CAM. Okay, now here computer-aided manufacturing, this is the sequence, that is first CAD model we have to develop, then manufacturing model, then tool definition. Battery level low. आगे हाँ ठीक है, अभी चल रहा होगा. ओके, चल रहा है, पता नहीं चल रहा, देखने कैसे. इसको दूसरा सर्किट में डाल दो. ये भाग रहा क्या, समझ नहीं आता है. Okay, लग गया होंगे? Okay, now that is CAD model, and here that a manufacturing model, reference model is there. We have to give the tool definition, then you have to select the raw material definition, then workpiece geometry definition, we have to give the workpiece geometry. Then you have to select the cutting parameters here. So what kind of cutting parameters like feed, speed, depth of cut we can give here, and the tool type, tool angle, which kind of tool we can give, and the tool angle, tool diameter, everything we can give. After this, it will generate a tool path. So means the software itself is generating a toolpath here so that we can see the simulation of the particular product. Then post-processing. So the post-processing is a term here. So we can convert the high machine language which is obtained by the computer to G codes and M codes. So this is the post-processing. This post-processing depends on the depending on the various controllers we can go for the post-processing. Like we have the various different controllers like FANUC, FIDIA, Synumeric, High Numeric, Siemens, HMT. All these we have the so many controllers. Depending on the so many controllers, we can go for particular one control by using the post-processing techniques. So this converts machine language into the CNC, that is G and G codes as well as M codes. Once you get the NC code, that is G codes, G stands for generative codes, and M stands for machine codes. It is also called as miscellaneous codes, which controls the machine. G controls the geometry of the component. जारी अच्छा G stands for geometry जारी है इसका G stands for geometrical codes and M stands for miscellaneous codes, and finally whatever we are getting the NC codes, we can transfer that data to the NC machine, CNC machines, whether it may be the milling machine or turning machines. Then finally we can develop a desired product from the raw material. So it is a sequence of steps starting from CAD model to the CAM product. What are the various steps involved in this process? So this is about the CAD-CAM, integration of CAD-CAM. Now we can see with these pictorial graphs, with these pictures, we can see how this CAD model is converted into the finished product. So first step is CAD model. With the help of CAD softwares, we can generate. This is one example I have taken. What is that is impeller, turbine impeller. So this is one example I have taken. So first it is modeling done by the CAD software. Then tool definition, the green color shows. So here we are generated the workpiece material. In always CAD-CAM software, the green color highlights that is raw material. Okay. Now this is tool selected. Next, third step is raw material definition. For this material, what will be your raw material? So that is simple cylindrical round shape product. That will be your raw material. And fourth step is that is workpiece geometry definition. We are selecting the particular geometry. Means if you see the outer side, inner side, it is the original product. So we have to remove the material, outside material, so that we can develop this impeller product. So here that is workpiece geometry in fourth parameter. Fifth, we are giving the cutting parameters here. So we are giving the cutting parameters like depth of cut, feed, speed, and tool diameter, tool angle. We are all giving the parameters here, machining parameters. Then after this, the tool path generation. Here we can see virtually, we can simulate the tool, then how much material is being removed through the workpiece. That we can highlight. So that is the sixth step, that is tool path generation. Next, that is post-processing. As I explained earlier, post-processing is that is conversion of machine data into the G codes and M codes. That is tool path generation, that is CLS file. It stands for cutter location file. Cutter location file. And here the post-processing modeling is there. That is again, you have to select the particular controller. If you have the CNC machine with the FANUC controller, you have to select the FANUC control. If you are having CNC machine with Siemens controllers, you have to go for the Siemens controllers. Then after selecting this machine data file, it will convert into the NC program depending on the controller which you have in CNC machine. Okay. Then after getting this NC program, that program is fed to the CNC machine. So nowadays we have the directly we are converting the data into the CNC machine. Whereas if you go for the 3 decades back, the people were writing a program months together for this program, for this to machining. So that's why heavy demand was there that time to NC programmers. Nowadays there is no demand for the NC programmers because the software itself is generating the programming. Okay. This is the one beautification of this software. So there is no need of manpower for writing the program. Only the computer itself generates the NC codes. And in this, another one advantage is we can see the virtual machining simulation. That is tool path and collision check. We can see. That means how much material is removed and how much still material is there to remove the next sequence. So that is. So here these are the steps. Now just I want to highlight about commercially available CAM softwares. What are the various CAM softwares available in the market? So that is mainly that a major in many industries, the major software is that is Mastercam and GibbsCam, SurfCam. If you go for the integrated softwares, that is integrated means you can do designing as well as the machining. You can do the CAD as well as the CAM part also. And we can do the CAE, computer aided engineering analysis. So some softwares are there only we can go for the manufacturing only. That is called Mastercam, SmartCam, GibbsCam. We can do only the machining part. We cannot do the designing part here. If you want to have any very critical components, we cannot design in the CAD software, CAM software. So that's why we are having integrated software where we can do the designing as well as the manufacturing. Like integrated software is our softwares are Ideas, UGCam, Unigraphics, and ProEcreo, SolidWorks, SolidEdge. So these are all integrated softwares where we can do the designing as well as the manufacturing. Now the another I want to discuss in the CNC, that's CMM, coordinate measuring machines, how we can get the geometry of the particular component. That is types of CMM. We can have the manual CMM, motorized, and CNC CMM. Now I am highlighting only the CNC CMM, how we can measure a particular component and go for the machining. That is CMM. One, we have the contact mode, non-contact mode, and portable mode. Portable mode is very portable, where we can use those CMM machine and take it to the vendor side. You can inspect the whatever components if you are having very smaller components. And contact mode, we have the point-to-point scanning, continuous scanning. Non-contact is, that is example is laser scanning. Through laser scanning we can do. And portable is portable. We can take it to the vendor side and we can inspect the particular components. And the comparison between the contact and non-contact types, it is contact type is we have the accurate measurement, but it is a slow process, labor intensive, and cannot reach deep interior features. So if you want to go for very intricate shapes, we cannot go for this manual checking contact. If you are going for the non-contact type, it may be less accurate, but it is very fast. We can get the results very fast in the non-contact type. So you can see that this is coordinate measuring machine. So this is coordinate measuring machine. We have the 5 axis, that is portable probes. In probes, we have that element which takes the dimensions of the particular component. If you want to go for any curvature shapes also, we can just tilt this probe, and so that we can go for the deeper dimensions. And this is called very huge gantry type CMM. This is a gantry type. This is the probe we are using. This is the probe, and which checks the dimensions of the particular vehicle. So these gantry type CMM are used for the checking of surface quality of the automobiles. And this is, I told about portable CMM machine. If you want to check at vendor side, you can take this portable CMM machine and go for checking. And sometimes this portable is assisted with the robots. That is called robot portable CMM. You can see into the next picture. That is a robot. That is with the help of robot, we can go for the CMM checking. And this is one slide highlighting about the geometric modeling. And this is CAD structural analysis, where we can go over the structural analysis. If you want to see the cantilever beam stresses, deformation in the particular beams, what kind of stresses involved, and what is the deflection in this particular, if you apply the load on the boundary conditions, we can see the deflections, displacement, as well as the stresses, deformations. And thermal analysis, we can see, so temperature distribution in particular component, and what is the range between the this temperature. And heat transfer analysis also, in this also we can see the what is the temperature distribution at particular level. And this CAD CAM is used in the mold making. So this is one kind of example helmet product. For this, how we are developing the dice. That is, first we have to make a model of these dice with the help of CAD softwares. Then again we have to go for the machining through the CAM software. So you can machine so that you can have these cavities. This is upper die, this is a lower die. Then it is assembled on the pressing tonnage, where we can develop this product through the injection molding. So now advances in CAM processor. So that is computer aided manufacturing. Advances is rapid prototyping. That is latest. That is computer numerical control, robots, and FMS and RMS. RMS stands for, that is, reconfigurable manufacturing systems. In FMS, we can change the machines according to our product design. Similarly, in the RMS, we can reconfigure the machine system here. Here we are reconfiguring the machines. Here totally the machine system we can reconfigure in the reconfigurable manufacturing system. So that is the difference. It is the advanced version of FMS. RMS is the advanced version of FMS as well as CMS, cellular manufacturing system. So here that is CAM. So just now I highlighted, that is first design model, and first you have to take the design model, what you want to design. Then workpiece. For that particular developing model, what kind of workpiece required, whether it is circular, whether it may be rectangular, or you have to see the workpiece. Then you assemble this design model as well as the workpiece model. You can get manufacturing model, and you have to assign the machine here, set of manufacturing database. Here you have to assign the machine tool, whether this product has to be allotted for the CNC milling machine or turning machine. We have to select the machine work cell, whether it may be turning or it may be the milling. Then if fixture requirement is there, you can go for the fixture setup also. Then you have to select the tools. Depending on the workpiece design, you have to select the tools. So whether we have the drilling process, whether we have reaming process, milling process, turning, step turning, all this we have to see. Depending on this process, you can select the tools. If it is working, if you want to work on the lathe machine, we have to select the turning tools. If you want to work on milling machine, you have to select the milling tools. Similarly, all this. And you have to set up an operation. For particular product, you have to set the operation and define the NC sequences. If you want to develop any product, suppose if you want to develop one cylindrical bar, if I want to develop one step turning as well as knurling, drilling, I can go for the three process. One is step turning process, then face turning, step turning, knurling, and drilling. Four operations I can go here. So here you have to define the NC sequences. And after this, the process will generate a CL data file, which is in the form of APT. So this is the APT, that is also called as advanced programming tool, which cannot be understood by the CNC machines. So that's why this APT data should be converted into G codes and M codes. That's why the post process is required here. With the help of this post process, we can convert this APT data, that is CL data, that is also called as cutter location data, to convert into the G codes as well as the M codes. Okay. You can see this picture. This is computer numeric control. This is the controller we have. This is the Fanuc control system we have. Similarly, we have the psi numeric, Siemens, high numeric, and hidden hand. All these controllers we have. And it is one of the picture for the CMM machine. And this is the basic structure of CNC machine, where can we have the spindle, table, and hydraulic pneumatic system and programmable logic controller. With the help of all this, we can make a structure of CNC machine. And this is one of the pictorial view of the CNC lathe, CNC turning. Okay. This is the main headstock. This is tailstock, and this is the main tool post where we can use different kind of tools according to the design of the tool product. We can use the different tools for the machining. And this is the 5-axis machine, where we have the total 5 axes. The 3 axes are linear here. If you can see this figure, the 3 axes are linear. That is X, Y, and Z. These 3 are linear movement here only. All x-axis direction, y-axis, and here z-axis. Here the tool movement is shown in the y-axis direction. Normally, z direction will be giving tool direction. Here y-axis here shown, and A and B are the 2 rotational axes. It is A rotational axis along with the x-axis, and B rotational is along with the y-axis. So these 5-axis machining is required, where we can go for the very intricate shapes of machining, like B-splines, NURBS, non-uniform rational B-splines, NURBS, where we can have the very intricate shape jobs. For that purpose, we can go for the 5-axis machining. Just now highlighted, that is turbine impellers, turbine blades. We can go for this 5-axis machining. Had it been 3-axis machining, it is not possible to make a machining. So we can use another 2 additional rotational axes, that is 5-axis machine, to machine a turbine blades. So now I'm going for the rapid prototyping technologies. So here, if you see this figure, this is the man skull, the example of man skull I've taken. So this is developed by the RPT process. We can develop, there are 6 techniques are there in RPT. So namely, that is FDM, fused deposition modeling, that is FDM technique, 3D printing techniques. It is now latest is 3D printing, and inkjet, and LYM. LYM stands for laminated object manufacturing. SLA, selective laser sintering. This is stereolithography. SLA means stereolithography, and SLS stands for selective laser sintering. So there are many additional techniques also in this. So these 6 are major techniques: FDM, 3DP, inkjet, laminated object manufacturing, selective laser sintering, stereolithography. And now the RPT is, that is, objects can be formed with any geometric complexity without the need for elaborate machine setup. So the RPT machine itself is generating the final product of the component. So there is no additional need of machines, additional secondary operations required for machining. So the RPT machine itself is generating the final finished product. It is also called as near net shape modeling, near net shape method. Rapid prototyping system reduces the construction of complex objects, and the different RPT techniques are, that is just now I highlighted, that is stereolithography, shortly named as SLA, fused deposition modeling, FDM, inkjet, IJ, 3-dimensional printing, selective laser sintering, laminated object manufacturing. So these are the 6 techniques. So here this picture shows, so there are 4 kind of techniques. That is, first, input material. What is the input material we are giving for the RPT process, and what is the material we are using for the product, and where is the application of this process is there, and what kind of method we are applying for this product RPT. The first, I will take input. What will be input for this? So input is, that is, CAD model or surface or solid model. It may be in the form of solid modeling or surface modeling, and it is a physical product in the form of, that is, I told about the translators, that is STL file, that is standard triangular length file, IGS, that is initial graphic exchange specification, cutter location inch file, With this file, we can give the input to the data, that is in the form of STL, standard triangular language file, IGS, CLI. And next, if you are after giving the input, then we have to select the material. What kind of material you can select for the product? You can go for the powder process, you can go for the liquid process, and you can use input as a laminates, pellets, like paper, ABS, wax, then metals. These are the all input materials. And after getting the CAD model as well as the input process, we can develop the RPT product by the application of again 6 techniques. One is FDM, SLA, SLS, LOM, inkjet, 3DP. With the help of these techniques, we can go for the RPT. So again, in these six techniques, some techniques are using powder process, some techniques are using liquid process, some techniques are using solid process. So depending on the material, you have to select the process. Then finally, you have to see the application where these products are being applied, whether it may be the aerospace applications, automotive applications, biomedical applications, consumer product applications, all this we can see. And in this application, we can go for the design process, engineering analysis, and manufacturing all together. Then here method, whether it may be the which kind of method, whether it is joining method, cutting, gluing method, or single layer beam method, we can select this. So this is the circle shows about the 4 elements: input material, and what kind of input material we are using, input method, input material, and applications, and the process with method. Out of 6 methods, you can select any one. So here that is CAD. The design part must be in the form of CAD modeling. That's why to know about the RPT, we should know the brief about the modeling. If you know the modeling, then only you can develop a product. Modeling means with the help of CAD tools like CATIA, IDEAS, ProE, Unigraphics, you can develop a model, physical model. Then you make into the form of IGS file or STL file or CLI file. Then you import this model into the RPT process. Okay, import the model and give the input material, maybe in the form of powder form, maybe liquid form, maybe solid form. Then you can find a prototype. You can build a prototype finally. So that is CAD file is in the form of STL, that is standard triangular language, and IGS in the form of initial graphics Excel specification. Then finally you can build a prototype model. So the advantages of RPT is it reduces the product development time and cost, and get products to market sooner, and to enhance the communications between marketing, engineering, manufacturing, and purchasing, and present physical model at critical design reviews. Whatever the critical design model we can develop in though whatever it is not possible even in 5-axis machining, so that can be modeled and manufactured in RPT process. These are the very intricate shape products can be developed in the RPT. One the disadvantage of RPT is we can make some size limit is there in this process. Only size limit, depending on the size limit only we can develop a product. If you want to develop very big size product, we cannot develop. Of course we can develop, but for that machine should be very the dimension of machine should be very large, and the cost also high for that. And it present physical model at critical design reviews, perform functional prototype testing before committing to tooling, and generate precise production tooling. So whatever the precision finish we are getting through the RPT, so that is 0% error, and it is error free from the other methods. And this is one example of RPT prototype machine, that is SGC 5600 method process. And some applications are engineering ceramic parts. That is, if you see these 3 products, this looks very near net shape forming methods. The first one is made by the paper laminated object by using the LOM process, that is laminated object manufacturing process. And this, the ceramic, that is plaster part made by 3DP process here. This is the plaster part. The input material is plaster, and the process used is 3D printing. Whereas in this, the ball within a ball, it is not possible even in the CNC machining or any kind of technique. Ball within a ball, it is not possible. For this, we have to go for the RPT process only. So these kind of intricate shapes can be developed in RPT process by using the 6 various techniques like 3D printing, SLA, SLS, LOM, FDP, 3DP, all these processes. And some scientific applications, we can see the model of a skull fabricated using 3D printing process. So this kind of finishing can be done only by the RPT process. And anthropological model of a skull made by stereolithography for study of human remains found in gemstone. This is also by 3DP process. And if you go for the any molecular models, see, you know about the DNA, that is deoxyribonucleic acid, DNA. So it is having very curvaceous shapes. Okay, this kind of shape cannot be developed by the CNC machine or any non-conventional machining, any conventional machining. So it is only applicable with the RPT process. That is protein. That is stick model of Watson Crick, that is DNA fabricated using the FDM process. And this is nylon alpha carbon backbone is done by the FDM model only again. And now the another application of RPT is that is in medicine and dentistry. So in dental applications also they are using the part is replaced by using with the help of RPT process. Like we are using the titanium alloys for this. And this is the RPT is a technology which uses digital data to construct models, prototypes by layer by layer. That's why it is also called as the layer manufacturing method. It is the forming, the material is forming by layer by layer by layer by layer. The layer of thickness of layer may be some microns. So it is forming by layer and it is building up the material. So that's why it is also called as layer manufacturing method, LMM. The creation of the model prototype begins with a solid model designed using the CAD software. That's why the minimum basic idea is the user should know about the CAD. The different CAD softwares are, that is ProE, CATIA, Unigraphy, all these things. And it is the most common technique used to fabricate physical objects directly from CAD data to the sources, CAD data sources. These methods are unique in that they are add and bond materials in layer to form the objects. That is by the name LYMM. And what are the rapid prototyping technologies? What are the various technologies? So that is rapid prototyping process are a relatively recent development. The first machine was released onto the market in the late 1987. And a more accurate description would be layer manufacturing process. An alternative term is freeform fabrication process. So these processes work by the building up a component layer by layer with one thin layer of material bonded to the previous thin layer. The layer thickness may be sometimes in microns. Okay, these are several different processes. So that is different processes are stereolithography, laser sintering, fused deposition modeling, surface solid ground curing, and laminated object manufacturing. And what are the strategic importance of rapid tooling technologies? What is the need of this technology? And strategic importance is for adding new technology to their products to differentiate, for forming alliances with their customers, and these are some benefits we have to expand this technology. And another question arises, that is, do we really need this RP process, and do we have another choices? If it is not being done by the RPT process, what is another alternative process is there or not? You have to check. So that is, do we really need RP process, or do we have other choices depending on your design of the component? And rapid prototyping is computer controlled additive fabrication. So so far we have discussed that is the material removal process. This is one kind of material additive process where we are adding the material to develop a product. In other cases, conventional machining, non-conventional machining, CNC machining, we are removing the material from the raw material and we are developing a desired product design. Whereas in this, we are adding the material to develop a product design. That's why it is also called as additive manufacturing process. That is, additive fabrication method are not better than subtractive ones. Additive technologies are instead complementary to the subtractive. So those are all subtractive process. This is additive process. They should be used if the institution calls for, that is complex or intricate geometry forms. Wherever the product is having complex and intricate geometry, there we have to go for the RPT process. And the simultaneous fabrication of multiple parts into a single assembly, so that we can go for the single product, then adding to those symbol we can make the assembly part. And multiple materials or composite metals in the same part. If you want to visualize in one part where is different color of parts, we can go for this RPT process. Okay, so multicolor, multiple materials of the colors we can use in the single product. So, and then what are the limitations? Now I told about the limitations. So limitation is one criteria here. Limitation is we have the size limit of the components. So we cannot go for the bigger of the product machining. Like if you go for in CNC machining centers, we can go very big dies so that we can machine. But in this case, it is not possible. It is having the size limit. It is depending on your RPT machine size. Okay, here the one disadvantage is stage stepping is sometimes it is not having smoother finish. We have some stage stepping, like stage stepping, three-dimensional printing. So if you see this multiple colored component, we have some extruded portion that is called stage stepping. But some amount of material is protruded here. Like if you see for the forging component, forging design components, we have the excess material is removed by the trimming die. Okay, we can remove the trimming dies. We can use the excess material is called as a flash there in the forging technology. Whereas here it is same thing, stage stepping. Okay, the excess material is called as a stage step. This is one disadvantage. This is also same stage stepping formed by the various techniques. This is inkjet technique. This is multi-jet modeling technique. Whereas in the previous case, this is stage stepping is formed by the stereolithography process. Whereas in this also, that is a three-dimensional printing process. In this, that is, if you can see this is the stage step. It is formed by the MJ multiple jet modeling. And this is by the inkjet modeling. And how complex does the geometry have to be to require rapid prototyping? So is there again some limitation for the complexity of the object also again? How complex does the geometry have to be to require this rapid prototyping? So that is, so we have some limitations in the geometry also. So this you can see, so complex or compound shapes are best fabricated using rapid prototyping. Some small desktop milling machines, where some small desktop milling is not possible by the other processes, where we can develop by this RPT process, like prototype model for this it is required. The materials are, I explained to you, that is plastic, other materials, paper, or other parts. And these are some applications in ceramic parts and scientific applications I highlighted already, and molecular models and in dental applications. So this is one of the last slide I want to show. So the Guinness record in rapid tool creation is, that is through Pro Metal software, the maximum size is, that is 740 by 500 by 60 mm. That is 740 mm length, so 500 breadth, and 60 mm depth. This part is made by using so far this RPT process. This was the higher dimension part so far they made. This is one of the Guinness record in the RPT tool creation by using the Pro Metal software, rapid tool software. So that's why in this the limitation is size limit is there. We cannot go for the bigger size production of the components. Okay. The benefits of rapid prototyping technology include that increased visualization and detect design flaws and time and cost saving, of course, innovation of new things. So these are some benefits we have in the RPT. And this kind of models Ganesha model can be developed by the CAD, and we can develop this kind of Ganesha using the input material given to the RPT machine. We can develop this Ganesha model. So This is with this I end this lecture on rapid prototyping. So this is a brief introduction since it is a new technology. Other competitively in this manufacturing area, I highlighted about this rapid prototype technology. So with this, I will end this lecture. Thank you. Thank you so much. चाय के लिए बोल दीजिए मैडम को. हेलो. हेलो.
बोलो कोई क्वेश्चन चालू हो रहा ना any query from RIT no sir
Okay. If no queries are there, we can have a tea break. That is 11:32. 12, na madam? 11:30 to 12. After 12, again we assemble here for the next session. Okay. Thank you. Thank you, one and all. Again, we assemble at 12 o'clock here exactly. चलो सर. मन्ना साहब आए नहीं है. मन्ना साहब.
है ना सर? ओके सर, थैंक यू सर। और क्या, अगर वो फीडबैक करते इसी टाइम पे करेंगे हम लोग।
बात कर लें. Okay, welcome back to the next session. Hello. All nodal centers are connected right now, I hope. Hello.
Yes, sir. Hello.
Okay. Now we'll start the next session, that is 12 to 1:30 the session, and after 1:30 we have lunch break 1:30 to 2:30. Again 2:30 we have another lecture by Professor Sarabjit Singh, that is 2:30 to 4 o'clock. Now we'll start the next session, that is Since the expert is not there today, we'll just take the one video. बोलना पड़ेगा ना उनको, बोलना है ना उनको, एक्सपर्ट नहीं आया ऐसे करके. हाँ हाँ. Okay, this section, in the next session, since the expert is not available, he has not arrived. So till he comes, we'll start this one electrochemical machining, that is lecture by NPTEL. So just to see this ECM video, and till he comes, we can see full screen. हाँ? ये वाला. अच्छा, आ गया. वॉइस और करना है क्या? मैक्सिमम
Good morning. Welcome to the class on manufacturing process 2. Today we are going to discuss on electrochemical machining. I am Dr. Soumitra Pal. This belongs to the module number 9 on non-traditional manufacturing processes. This is lecture number 9.5. Before starting the actual lecture, let us go into the instructional objectives. Instructional objectives, as you know by now, are the points or topics that you are going to learn once you go through this lecture. In today's instructional objective, once you go through the lecture, you'll be able to identify the electrochemical machining, which is in short known as ECM, as a particular type of non-traditional processes. Already we have covered a few non-traditional processes. You know, abrasive jet machining belongs to mechanical group of non-traditional processes. Similarly, ECM you'll be able to associate with a particular type of non-traditional process. Once you have done that, you will also be able to describe the basic working principle of electrochemical machining. You will be able to draw the basics of ECM so that you can describe the working principle along with figures. In electrochemical machining, electrodes are used for machining. So across the electrode, there will be potential drop. So you would also be able to understand and schematically draw the tool potential drop. Schematics of those application areas. So this briefly describes the instructional object. Now let us go into the classification of non-traditional machining processes. This is your 5th lecture on non-traditional machining process module. So already you have gone through quite a few of them. And in the process, you have learned that there are mechanical processes, there are electrochemical processes, and there are electrothermal processes and chemical processes. Before today's lecture, we have already covered electrodischarge machining in the previous lecture. We have covered abrasive jet machining, ultrasonic machining, water and abrasive jet machining, which were belonging to mechanical process. And today, our aim is to understand the basics of electrochemical machining, which belong to electrochemical process segment. Within that process segment, there are two more processes. One is electrochemical grinding, another one is electrojet drilling. However, today we'll concentrate on ECM or electrochemical machining processes. Now let us come into the electrochemical machining process. In electrochemical machining process, like any other process, we require a workpiece as well as we require a tool. So this is my tool and this is my workpiece. They are immersed in a solution just like the electrodischarge machining. But this solution is not dielectric like electrodischarge machining. This solution is that of an electrolyte. Typically, sodium chloride salt is used to prepare the aqueous solution and the electrolyte. What is electrochemical machining? Briefly, it is just the opposite of electrochemical deposition. This is a controlled anodic arc, canodic dissolution. So this is my workpiece. So this was my workpiece, and this is a anodic dissolution. So this is controlled anodic dissolution. So if you look here, the workpiece is connected to the positive terminal, and your tool is connected to the negative terminal. What is the next point? We have already covered. Tool is my cathode, and workpiece is my anode. There are other characteristics of ECM process as well. Typically, the voltage which is you apply is a low voltage, it's low potential, but the amount of current which passes through this particular electrochemical cell is rather high. Now, there is a machining gap. Initially, the machining gap would be rather high, but during steady state operation, the tool has to be fed continuously so that a specific gap can be maintained. And as we have already said, the whole thing has to be immersed in an electrolyte solution, and sodium chloride or sodium nitrate, these aqueous solutions are the typical electrolyte solution which are used in electrochemical machining process. Now, let us schematically see what happens typically when someone is trying to machine a ferrous material. Different types of materials can be machined, but for today's example, schematically, we want to show what happens when it is a ferrous material. So let us come to the graphics. So this is describing the electrochemical process, and this is my workpiece, and this is my tool. Okay, and once we apply a potential difference, then what happens? Because of electrochemical dissolution, this is my electrolyte, this is my electrolyte, and the electrolyte could be sodium chloride electrolyte. So what happens? As because it is aqueous solution, in this particular electrolyte, you would have chlorine atoms. So these are your chlorine ions. Similarly, you would have sodium ions. You would also have hydroxyl ions because water will dissociate. And once the cell is switched on, once current is passing through it, that's because the workpiece is made of ferrous ions. Ferrous ions will react with chlorine ions as being indicated here to form ferrous chloride. They can also react with hydroxyl ion to form ferrous hydroxide. What happens to the hydrogen ions? These are the hydrogen ions. Hydrogen ions deposit. So they will go towards the tool material which is connected to the negative terminal, and hydrogen gas will be formed. So in summary, what happens in electrochemical machining process? I have a workpiece, I have a tool. I apply a particular potential difference. The tool is connected to the negative terminal and the workpiece is connected to the positive terminal. And the whole, as well as workpiece and the tool, they are immersed in an electrolytic solution. Typically, sodium chloride or sodium nitrate solutions are used as the electrolytic solution. I apply a DC current, and the typical voltage applied is 235. As because it is sodium chloride solution, the aqueous solution, I would have sodium ions and also have chloride ions. And once the cell is switched on, iron will come out of the workpiece and react to form sodium chloride or sodium hydroxide, and hydrogen will evolve from the gap. In this way, due to controlled anodic resolution, we will get machining on the anode or workpiece. Now, you have already seen this is my workpiece, which is anode, and this is my tool, which is cathode, and I am applying a potential difference between them. Let us try to study how that potential difference drops a particular ECM cell. What we have here, this side is my anode, and this side is my cathode. So the total potential drop over here is called the anodic potential drop, and the total potential drop here is called the cathodic potential. What is this separation? This is the separation or distance. This is the distance between my two electrodes. This is cathode, so this has to be my tool. This is anode, so this has to be my workpiece. And this is the distance of separation. Okay. Now, first drop is the anodic potential drop at the anode, and similarly the cathodic potential or cathode potential drop at the surface of the cathode, which is followed by the activation over potential. We require a bit of over potential to establish the flow of electrons to the cell. This is the activation over potential. Then you have ohmic potential drop within the cathode and anode, and similarly you have the concentration potential drop, because once electrochemical machining or deposition starts, there will be some concentration gradient near the electrodes. And then from this point to this point, you have the electrolytic drop over the almost complete separation distance between my cathode and anode, or in other words, tool and workpiece. So in this way, the potential drop occurs in electrochemical machining. To have electrochemical machining, I have to provide a potential so that all these potential drops can be achieved and gone beyond, so that there is an electrolytic drop which drives the cell of machining process. Now, let us come to the process parameters. As you know, if you cannot identify the process parameters, understanding the basic process becomes difficult. Without knowing about the process parameter, you cannot optimize, you do not know what is the effect of a particular process parameter on one of the most important machining characteristics, that is material removal rate or product quality. So we need to understand what are the process parameters first for any machining process. And today we are going to do that for electrochemical machining. As we said, one of the major area or major item in electrochemical machining is the power supply. That means what kind of power we are going to give. Generally, DC power will be given. We have already identified it is a low potential. The voltage applied is rather low, around 2 to 35 volt. However, the current capacity of your power supply has to be very, very high, around 50 to 40,000 ampere. More so, the process is identified not by the current, but by the current density. Current requirement is very much important for the machine manufacturers, but current density, this particular term, is very, very important as far identifying the process is concerned. And the current density, as you can see, is around 0.1 ampere per millimeter square, 5 ampere per millimeter square. So current density is nothing but the current divided by the area of the electrodes. Now we have already understood that there has to be a working gap between the electrode and the workpiece, and that working gap is around 0.1 millimeter to 2 millimeter. Just like electro-discharge machining, as we have discussed, in ECM as well, there is some amount of overcut. When we go into the schematic of the actual drawing, we will once again show you how to control that overcut. As we said, to maintain a particular working gap, the tool has to be fed, and it has to be fed with a particular feed rate, which varies in terms of 0.5 to 15 millimeter per minute. You can see the feed rate is rather high, 15 millimeter per minute. So the material removal rate in electrochemical machining will also be high. Electrode material can be copper, brass, and bronze. It can machine any material which is electrically conductive, irrespective of their mechanical properties. And the tool material are typically the copper, brass, or bronze. Surface roughness obtained are very good. It is as less as 0.2 to 1.5 micron, but quite often it is rather less.
Can I
Once again,
copy
we
this
have
material?
the electrolyte. So electrolyte also plays a significant role in electrochemical machining. Typically, either aqueous solution of sodium chloride or sodium nitrite is used. A temperature is required to be maintained and a flow rate has to be maintained because during the machining process, sodium, if you are machining iron-based alloys, iron chloride or iron hydroxide are forming during the machining process. Those are sludges. If they are not removed continuously, your molar concentration of the electrolyte is going to change. Thus, you need to have a substantial flow rate so that those sludges can be removed continuously. And for that, you also require a pressure. Typically, the dilution is around 100 grams to 500 grams per liter of water. So 100 grams of sodium chloride is formed with 1 kg of water or 1 liter of water to get a particular electrolyte in for electrochemical machine. Now let us come to the characteristics of electrochemical machining. The characteristics of electrochemical machining will be talking about what are the typical properties required of wood material and work material. Tool and work material, both of them are to be electrically conductive. So it is very similar to your electro-discharge machining. Just as in electro-discharge machining, your tool and work materials are to be electrically conductive. Similarly, in electrochemical machining, they are to be conductive. If you remember, as far as abrasive jet machining, water jet machining, abrasive water jet machining, and ultrasonic machining was concerned, there the domain of the energy was mechanical in nature. Thus, you do not require the material, the work material to be electrically conductive. But here, as well as in electro-discharge machining, they are to be electrically conductive. What is the next characteristics? The material removal characteristics. Material removal occurs by atomic level dissolution. As we said, electrochemical machining is just the opposite of deposition, electrochemical cooling or deposition process. So it occurs due to atomic level dissolution. As because it is atomic level dissolution, the next point is very, very simple to understand. You get a very, very excellent surface finish. As because it is atomic level, surface finish expected to be very good. And here you can get a surface finish as low as 0.1 to 0.2 micron RA value, which is very, very good. Now let us come to the another point. In any kind of mechanical grinding or machining process, or even in electro-discharge machining process where there is a lot of thermal effect, you will be getting a lot of temperature damage. So there will be residual stress. But in electrochemical machining, almost stress-free machine surface are obtained. There is absolutely no residual stress. So in strategic sectors where the material machine component should not have any residual stress, this is a very good solution, electrochemical machine. And as well as there is no thermal damage, or rather as because there is no thermal damage and as because the dissolution is atomic level, we get residual stress-free machine surface. Now let us come to the modeling of material removal. Till now we have discussed around 4 different non-traditional machining processes. And in all those non-traditional machining processes, we have tried to model material removal rate. Because material removal rate determines how fast you can machine, so how much will be your machining time, so that in turn will determine what is your productivity, even what will be your profit rate and all those functions. So it is a very important phenomenon to understand, so that later on it is, as because it is later on related to even techno-economical viability of that particular process. So now let us come to the modeling of material removal rate in electrochemical machining. We have already understood material removal occurs due to atomic dissolution, and as we know, electrochemical dissolution is governed by Faraday's laws of dissolution. So this is a very simple law and which can be used to model electrochemical machining process. What the law says? It says amount of electrochemical dissolution or deposition. This law is not only for dissolution, it is equally applicable for coating process or deposition process. So amount of electrochemical dissolution or deposition is proportional to what? Amount of charge that we pass through the electrochemical cell. This is the first statement of the law. What is the second statement of the law? Once again, amount of material deposited or dissolved, in case of machining it will be dissolved, the amount depends on or proportional to something which is called electrochemical equivalent. equivalence, which is typically denoted in the industry by ECE. And what is this ECE? ECE is related to the ratio of, it is the ratio of atomic weight and valency of resolution. So we have two laws, and we need to use these two laws so that we can come up with a expression for material removal. Material removal rate is a very, very technical characteristics, and we want to use these two basic laws to try to come up with an expression for material removal. So what was the first statement? The first statement was amount of material dissolved or deposited is proportional to charge. This is the statement given in the mathematical form. Mass is proportional to charge. What was the second statement? Second statement said the amount of material is proportional to electrochemical equivalent, and which is the ratio of atomic weight by valence. So now I can combine this expression as well as this expression, these two, so to say, mathematical expressions, to get the third one, which says combining this, mass is proportional to charge as well as atomic weight divided by valence. So it's a very nice expression. Once again, charge is nothing but current, how much current I am passing for what duration. So IT into atomic weight divided by valence. This can be expressed in an equation from not proportionality form, like amount of material dissolved or machined or deposited is equal to I amount of current passed into time into atomic weight divided by valency, and now I have a constant, which is the Faraday's constant. And Faraday's constant, the value is 96,500 coulomb. Okay, so this is my constant. So I can say if the total amount of charge passed is 96,500 coulomb, then amount of material removal will be exactly equal to the atomic weight divided by valency. So if your atomic weight is 10, valency is 2, your mass dissolution will be 5 grams. Now, this is the amount of mass dissolved. Now we want to get material removal rate. Material removal rate, if you remember, is typically expressed in volume, millimeter cube per second or millimeter cube per minute. So, amount of material dissolved divided by time, that gives kg per second, divided by density will give you material removal rate. So, the earlier expression was ITFV into A, that stays, which divides by T by rho. So you get this particular expression. So material removal rate ultimately is proportional to current, it is proportional to atomic weight, it is inversely proportional to the valency, it is inversely proportional to density, and there is a constant which is Faraday's constant. However, this particular modeling that we have done is for elemental material. That means if you are machining only nickel using electrochemical machine or only iron using electrochemical machine. But as you know, in engineering application, generally elemental materials or metals are not used. Typically, alloys are used. What are alloys? Alloys are typically the solid solutions of different elements. Say for example, steel is an alloy. Inconel 718 is an alloy. Titanium 6Al4V is an alloy. So all these are alloys where there are different types of materials. So let us try to develop the MRR model for a typical alloy or any alloy for that. So modeling of material removal rate for engineering alloys where you expect more than one element. So I have denoted atomic weight by AI, valency by VI, and weight fraction by alpha I, meaning thereby there could be, I could vary from 1 to n or 1 to 3. There are 3 different elements. Now, for passing a current of I with a duration of t, there will be a total volume removed, which is gamma A. Okay. Now, what is that expression for volume removal? Gamma A into rho into alpha I, where which one is the weight fraction, would be m. What I am trying to say is that if you pass a current of I over a time span of t, you remove a total volume of gamma A, out of which mi, or for that matter m1, is the total amount of dissolution of the first element. How much is that? m1 is equal to gamma A times rho times alpha. Now comes the same thing, mi equal to Qi into Ai divided by F into Vi. This was the expression that we have obtained earlier as well. So as if to remove M1 amount of material of element 1, you require Qi or Q1 amount of charge. So Qi can be once again expressed as this, and using the expression available here, you can get an expression like this. Now what is Qi? Qi is as if the amount of charge required to machine the iron. So how much would be my Qt? It is very simple. If I know how much is my Q1, Q2, Q3, Q4, I can simply sum up to get the value of Qt. However, Qt is also I into T. If I pass 1000 ampere of current for 10 seconds, I know how much is the total charge. And that is sum of all the charges. And I have the expression for one charge, so I can simply sum it over all the charges. To get the material removal rate as gamma A by T, because this was the volume removal, I took this much of time, so I can simply get the material removal rate like this. Now, if you compare this material removal rate, which is for an alloy and for an element, they are very similar. How they are similar? Material removal rate for an element is proportional to current. Here also it is proportional to current for an alloy. It is proportional to rho. It is inversely proportional to. Here also it is inversely proportional to. So where is the difference? Difference is, in case of elemental, this is proportional to ratio of A by nu. But here, because it is an alloy, there it goes in the denominator and summed up. Why it is summed up? Because you have different weight fraction and different valencies and different atomic. Otherwise, if you look at the structure, they are very, very similar. Now, we have got the expression of material removal rate, but during machining process, the tool is somewhere here. Where is the tool? During machining process, this is my tool and this is my workpiece. During a particular instant, there is a distance separating them, h, and I am passing a current I through the cell over a time span dt. And when I pass a current of I over dt, the total charge involved dq is I into dt. And because of that passing of charge, there is further dissolution of this amount. So what happens? Over time, this distance is going to increase. So this is called dynamics of electrochemical machining. And as if we are not feeding the tool, the tool is fixed here, it is not moving. So we want to study what happens to this gap if the tool is not given any feed, no feed condition. That's what we want to study. How would you study? This is the statement, I amount of current is passed over a time dt, and in the process we get a dissolution of dH, and over an area of S. What is that area? If you go back to the previous one, this is the area S, that is the area of the workpiece. We already have the expression of I. What is that I? I is nothing but the ohmic drop V by R. This is my resistance. So resistance can be written as resistivity into H, that is the distance, into S. So this is my expression of I in terms of voltage drop, in terms of area of the electrode, resistivity and the distance at time t equal to 0. So this is the expression of material removal rate, IA by F into rho into V. This is the standard expression, but material removal rate is also dH by dt into S, dH dt by S, because this is the rate at which the material is being consumed or dissolved into the area. So I can write dH by dt in this particular form. What is the difference in this form? Here you have a suffix of x. X denotes that this is the equivalent atomic weight of an alloy, and as well as this is the equivalent valence. Nothing more than that. So in that way, I can further simplify dH by dt into this. And in this particular expression, what you can see is that this part is a constant. So this part is a constant which has been taken out here, and we can say this constant is C. So your dH by dt or dH dt becomes C upon H. So dH dt becomes a function of H, and it is an inverse function. So this is your C, value of C, and further, for an alloy, value of C can be written like this. This was for a particular element, and this is for an alloy composition. Now let us try to integrate this particular equation to see what happens actually. So this is your equation. We need to integrate to see how H changes with time. What was H? H was the separation distance. So I can integrate between initial and some value H1, and I get the equation like this. If I plot this equation, what happens? This is something like this. This is what? This is your H0, the initial set separation between the tool and the workpiece. As time progresses, time is your x-axis. As time progresses, the H increases in a parabolic manner. Why it increases in a parabolic manner? Because that is dictated by this particular equation. So what happens? As it increases, the distance between the tool and the workpiece increases, and there is less amount of material removal gradually. Had the material removal rate been constant, this would have been a straight line. That is not the case. Which says this particular expression tells us, or this figure tells us, that if there is any field given to the tool, gradually the work distance between the workpiece and the tool is going to increase, and the material removal rate is going to fall. This is not a good thing. So we have to do something so that we can maintain the material removal rate. So for that we need to give a feed to the tool. That's what we are going to analyze now. That is dynamics of electrochemical machining with feed condition. Tool is no longer fixed, it is being fed. So generally, it is fed with a feed rate of F, that would be millimeter per second. So earlier, your expression was dH upon dt C by H. It's the same expression we are using, but this was under no feed condition. So now I am giving you feed. So your dissolution will be dH by dt. Now, under steady state, it is expected, but there will not be any change in the distance between the job and the workpiece. If there is no change in the distance between job and the workpiece, under steady state condition, this can be equated to the 0. And if it can be equated to 0, C upon H, that becomes equal to F, or F becomes C upon H. Now we need to see what happens to that steady state gap H star. So what is H star? H star is the steady state gap. Under steady state condition, it will be dictated by C and F. That is, C is basically related to how much voltage you apply, how much current is passing through the cell, what is the alloy you are machining, and F is a set parameter on your machine. Okay, so on that H star will depend. Now this brings us to a very, very difficult question. What is that question? For a given value of feed and for a chosen value of current and all other parameters, I get a H star of 1.5 millimeter. My question is, how do I ensure that whenever I am starting electrochemical machining, all the time that gap, initially that gap is 1.5 millimeter. What happens if I cannot maintain the initial gap of 1.5 millimeter when my calculated steady state gap is 1.5? It's a very tricky question. You have set all the parameters, undergone rigorous courses in electrochemical machining, and come up with the steady state value of 1.5. How do you ensure the gap is 1.5? Or what, is there any point spending time in setting the initial gap to 1.5? That's what we are going to check. First of all, is it possible to set H0 equal to H0? It is possible, but it takes time. So should we do it? That's what we want to analyze. So once again, this is my basic expression, dH by dt equal to C upon H minus F, where F is the given field and C upon H is the resolution, that is under no field condition. Now we are going to change the variable domain of H as well as D by variable transformation. So we are basically transferring the domain. We are making them non-dimensional, nothing more than that, so that we can get a non-dimensional expression of ddt prime H prime, and that non-dimensional expression is also related to ddt of H, or that the rate at which the anode is dissolving. And now what we need is, finally, we want to see how this H prime is going to change, and that we will be trying to get by integrating this particular equation. We'll be integrating it between t equal to 0 to t prime and h equal to h0 prime to h1 prime. And if we integrate it, we get an expression like this. And this is the way the curve change. What is there in the curve? It is a very interesting curve. This is my time or non-dimensional time, and this is my non-dimensional final gap. What is this? This 1 is the non-dimensional steady state gap, which happens to be 1. Irrespective of whatever is your initial value, whether it is 0, 0.5 or 5, this is for 0 and this is for 5. Irrespective of your initial gap, gradually over time, the same steady state value we achieve. This is a very good information for us. What was the problem? If you go back to the problem, you would understand. Our problem was getting or setting the machine to a particular value of initial gap. And we were trying to understand what happens if we cannot set it. And what is the result? After analysis, we find that the result is something like this, which is very, very in our favor. Irrespective of whatever be the initial gap, final value is saturating at 1. That is the equivalent gap. Thus, we can say, irrespective of the initial gap, h prime bar or would be 1 or h would be equal to h star. So it is very, very evident. So from that, we can get a value of feed rate, which has to be set on the parameters. I hope you have got the point. H prime has to be 1. So H prime was nothing but H upon H star. You remember, H star was C upon F. So this is the transformation. So from this expression, we can get a value of F, which we have to set on the machine. And that depends on what is the voltage you are going to apply, what is the resistivity, and what is the alloy composition. F depends on that, as well as it depends on the value of H. And ultimately, you can get a value of F when this H can be cancelled out. How it can be cancelled out? We know that I equal to Vs by RH. I equal to Vs by RH, and here I am getting an expression by V upon RH. So I can measure the current, and I can set the current on the machine. I know how much is the surface area. This is basically the material, so I know that. So how much will be the feed that has to be set? Once again, how much will be the feed that has to be set on the machine depends on your current which you are setting. It depends on the area of the electrode which you can measure, and it depends on the density, valency, and the atomic weight of the material you are machining. So this is also known. So that you can set, you can get a particular value of F. And this is basically the rate at which material is removed at the workpiece surface, typically expressed in millimeter per second. Now let us come to the equipment. What are the modules that are used in electrochemical machining? Typically, we have a power supply, we have an electrolyte filtration and delivery system, we have a tool feed system, and working tank. Now, what are these? This is my electrolyte tank. This one is my electrolytic tank. This one. There I have a motor and I have a pump. So it goes through a pressure reducer as well as a flow meter and a pressure gauge, and it enters the tool. Here the tool is a hollow tool, and this one is the insulation on the tool. You may ask me why we are going to provide insulation on the outer surface, because we do not want an overcut. So the electrolyte comes like this and moves over the working surface. Gradually, at this particular places, you would have electrolytic dissolution. What is this? This is my power supply. So this is the positive terminal. Sorry. This is my power supply. This is the tool. So this is your negative terminal, and this is your workpiece, which is the positive terminal. You require a tool feed system because this gap has to be maintained. So you require a servo system for feeding the tool. Once machining has been done, sludges will be collected here, like iron chloride or iron hydroxide. So these sludges are to be removed. So they are taken out by a valve, and this is a centrifugal filtering unit or a separation unit. After separation, sludges are kept here, and the electrolyte is fed back into the system. So this is the basic modules of electrochemical machining. And to summarize once once again, you require a power supply, filtration unit, tool feed system, and working tank. These are the basics of basic module. Now let us come to the application of electrochemical machining. As we have already said, under the characteristics of electrochemical machining, it requires electrically conductive work material. As long as your work materials are electrically conductive, irrespective of their mechanical properties, like what is their Young's modulus, what is their hardness, it can be machined. What kind of machining operation can be done? Let us come to that. Die sinking can be done in electrochemical machining, very similar to your EDM die sinking. Profiling and contouring can be done. This is another very important application area. Trepanning can be done. Electrochemical grinding. Electrochemical grinding. This is a technology in its own right. Drilling can be done. And another very, very emerging area of electrochemical machining is micromachining. We are not going to address that, but out of these few applications, now we are going to go into the schematics. What is die sinking? Die sinking is shown here. This is your tool material and this is your workpiece. So gradually the tool is fed in this direction so that you can get a negative impression of the tool on the workpiece. Problem of overcut. Once you give insulation, there would not be any electrochemical action here. We want the electrochemical action to be restricted just below the tool surface. However, you cannot restrict it here, so there is some machining or overcut. At least by insulation, the overcut can be reduced to some extent. And this way, you can drill a hole. The hole can be a large hole as well as a small hole, or it can as well be a complex shape. Now let us come to the trepanning operation. Trepanning, you want to make a large hole and you want to remove the center piece. Technology is very similar. Electrolyte is forced to this, and once again here also you can put insulation, and this way very large holes can be trepanned. Now let us come to the quiz part of it. Quiz part of it, any of these lectures are very interesting. They are not exactly knowledge-based things. You need not have to memorize things to answer these things. It has been designed in such a way you can reason it out. So let us come to our first question. What is our first question? For electrochemical machining of steel, so my work material is steel, what has to be used as an electrode? What are the options? Option is kerosene, sodium chloride, deionized water, and nitric acid. Which one should be used? You already know that kerosene is typically a dielectric medium, and it is used as a dielectric medium in electrodischarge machine. It is not going to ionize very easily. You require much higher voltage to ionize. So kerosene is definitely not used as an electrolyte. Deionized water. This is not tap water. Deionized water is once again a dielectric. It is used in bare medium. So, as because this is dielectric, as because it is deionized, it does not have so much of ions, so it will not ionize easily. It requires higher ionization potential, so you don't use it. So ultimately, you are left with sodium chloride or nitric acid. Both of them can be used as an electrolyte, but nitric acid as such reacts with most of the material very, very violently. You cannot control the anode choice is ultimately sodium chloride, not nitric acid. So in this way, for most of the questions, you can reason out and get to the correct answer. Let us come to the second one. Material removal rate in electrochemical machining depends on. We know electrochemical machining process can be very easily modeled by Faraday's laws of electrochemical dissolution. We also know electrochemical machining process is a non-traditional machining process. So material property, mechanical properties of the material doesn't really matter. So what are the options given? Hardness. Hardness of a material is very important in conventional machining, say turning milling, but does not matter as far as electrochemical machining is concerned. The third option given is thermal conductivity. Thermal conductivity quite often is important in non-traditional machining process. We need not throw it away. But if the basic process is thermal in nature, then only thermal conductivity comes into picture. Otherwise, thermal conductivity do not have any role. Say for example, in laser machining, thermal conductivity will play a role. In electro-discharge machining, thermal conductivity will play a role. But as we know, electrochemical machining is an electrochemical dissolution. Thermal conductivity has no role in that. Next one is ductility. Ductility plays role in conventional machining processes as well as mechanical non-traditional machining processes. So in electrochemical machining, there is no. So we are left with atomic weight. Why atomic weight? Why is it important? Why is this the answer? Because we know electrochemical dissolution follows Faraday's laws of electrochemical dissolution, Faraday's law, and that says your mass of dissolution is proportional to charge, and it is also proportional to electrochemical equivalent, which is nothing but atomic weight upon balance. So definitely this is the correct answer. MRR in electrochemical machining does depend on atomic state or atomic weight. Now let us go to the third and the fourth question. ECM cannot be undertaken for four options are given: steel, nickel-based superalloys, aluminum oxide, and titanium alloys. Out of those four options, steel is a metallic alloy and it conducts electricity. It's electrically conductive. Nickel-based superalloys, though their thermal properties are very high, the thermal conductivity is very poor, they are electrically conductive. Same goes for titanium alloy. Though their thermal conductivity is less, but they are good electrical conductors. So these three things can definitely be machined, because one of the basic requirement of electrochemical machining is that your work material has to be electrically conductive. So out of the given four options, the three options, steel, nickel-based superalloys, as well as your titanium alloy, satisfy that criteria. So what we are left with? We are left with only one candidate, which is aluminum oxide. We know aluminum oxide is a ceramic. You must be knowing by this time. This is also used for machining steel. This is used as a ceramic inserts, and they are electrically insulated. Thus, this is the answer. As because it is electrically insulating, electrically it doesn't conduct, it cannot be machined under electrochemical machining. So your answer is aluminum oxide. Commercial ECM, the next question. Commercial ECM is carried out at combination of low voltage and high current, low current and low voltage. Out of all these options, low voltage and high current is the answer, because to do the ionization in a salt solution, you require really low voltage. Why high current is required? The answer is once again M is proportional to Q. Either you pass high current for a short duration of time or very small current over a long duration of time. The first one is definitely economically much more beneficial. So the answer is low voltage, which comes from the technology, and high current, which once again comes from the techno-economic. Now let us go into the solved problems. Today we are going to discuss three different solved problems which represents the domain of electrochemical machining. The first one is in electrochemical machining of pure iron. So we are starting with a very simple assumption. It is pure iron. The material removal rate of 600 millimeter cube per minute is to be obtained or is required. Estimate the current required. So the estimation is very simple. We know MRR is nothing but is proportional to atomic weight, current, and valency, and Faraday's constant. So from that, if we put those values, This is in cc per second, so it comes here material removal rate. 56 is the atomic weight of iron. 96500 is the Faraday's constant. 7.8 8 is the gram per cc is the density, and 2 is the valency of dissolution of iron. So using this expression, you can very simply get a current of around 268.8 ampere. So there are two things to learn from this particular exam. What are they? One is how much amount of current is required. It is around 270 ampere. There is another thing to learn. It also indicates how much is the material removal rate, which is typically 600 millimeter cube per minute. We have two more problems and we'll go into them gradually. Next one. This is a bit more difficult problem. Composition of nickel-based superalloy is given. So it is having nickel, chromium, iron as well as titanium. Their percentages are given, their densities are given, their atomic weights are given, even their valency of dissolution is given. All these things are given. So what we need to calculate first is their density. What is the density of the alloy? And density of the alloy has been calculated using this particular expression. Once the density is known, density of the alloy is known, using the standard expression of material removal rate, we can get the material removal rate as 2140 millimeter cube per minute. And what is the rate of dissolution? In the problem, the area was given as 1500 millimeter square. So I can also get the rate of dissolution is around 1.53 millimeter per minute. Now let us go to the third problem. In ECM operation, it says pure iron equivalent gap of measured with the supply voltage. The over voltage is 2.5. Resistivity is given as well as set weight rate is given. So how to solve the problem? H star. We have to find out that expression. H star is the equivalent gap, which is C upon M. C we can calculate because all the parameters are given, but it has to be calculated as a function of voltage applied, which is V minus 2.5. In this way, you can find out how much is the voltage applied, which is 8.7. Here, in this particular problem, there is only one area where we face problem, which is this. This is the voltage. Over voltage was given as 2.5 volt, so the actual voltage is 8 minus 2.5. And from that expression, we have to get the actual voltage. So let us come to the summary of today's lecture. We have already gone through the electrochemical machining process, and now you can associate electrochemical machining as a non-traditional machining process. You have also understood the basic working principle of the electrochemical machining process. You can draw as well as find out what are the different potential drops. You know the material removal mechanisms of electrochemical machining, as well as you can model it. That is very, very important. You know that what are the process parameters, models have been developed. Dynamics of ECM is very, very important. That has been analyzed. And another important area is different modules of ECM equipment has been talked about, along with typical applications. So with that, we come to an end of today's lecture. Thank you so much. belongs to module number 9. I am Dr. Shobhit Pal from Department of Mechanical Engineering. Now let us go into the instructional objectives. After going through these lectures, you'll be able to list different configurational machine processes. Already we have covered some of them. Remember the previous lecture before that. You'll be able to differentiate water and abrasive water jet machine. You'll be able to list different things. What are they? You'll be able to list different water jet and abrasive water jet systems. You'll be able to list what are the different modules within abrasive water jet systems. List their applications, list their advantages. What are the materials that can be processed for abrasive water jet systems. Not only that, you'll be able to describe the functions of different elements or modules which are required to prepare abrasive water jet systems. Describe the mechanism of material removal process, develop models for mechanism of material removal, identify parameters related to product. Whenever you undertake any manufacturing process, you are basically developing a product. This product quality is very, very important. So you will be able to identify what are those product qualities, how the other abrasive water jet parameters vary. You'll be able to identify limitations of abrasive water jet in a manufacturing process. Have their advantages as well as limitations. Limitations are also very important. Moreover, the futuristic direction of R&D in the area of abrasive water jet machining will also become clear once we cover this particular thing. Now, in non-traditional machining, the different processes can be grouped depending on what is the energy source. Already, in the last lecture or the previous lecture before that, we have identified one such group is mechanical processes, one is thermal processes, electrochemical processes, and chemical processes. Say for example, we have heard about electro-discharge machining, laser beams. They are the basic energy source which is relevant for mechanism of material removal, thermal process, etc. Listed under that. Today we are going to cover, as I said, water jet and abrasive water jet. There, the energy source is mechanical. Similar processes under mechanical process are ultrasonic machining, abrasive jet. Today, we will be concentrating, as I said earlier, water jet and abrasive water jet. Now, what is abrasive water jet and water jet? Both of them we require very high pressure. So we require high pressure. So this is the pipe which carries the high pressure water. How high is the pressure? The pressure of the water is as high as 4,000 bar. We may question how much is 4,000? Typically in a 3-story building, if you have an overhead tank, then in the ground floor you get a pressure of around 1 bar. 4,000 bar is a lot of pressure. If you convert that to stress, general stress, 4,000 bar is around 400 kPa. Most of the carbon steel shear strength will be less than 4,000 kPa. So high pressure at 4,000 bar is rather very, very high. What is done with the high pressure water? High pressure water is allowed to come out of a small orifice. How small is this orifice? This orifice is really small. It is around 0.1 to 0.2 millimeters. So pressure energy of the water of 4,000 bar gets converted into the potential. So once the water comes out of the orifice, the water jet is formed. So water jet is available here. What is the velocity of this water jet? If we use Bernoulli's equation where we will be going between jet at a later stage, this velocity can be calculated as 1,000 meter per second. That means 1 kilometer per second. So if you have to go from Kharagpur to Calcutta, 120 kilometers at this particular speed, it will take only 2 minutes. So that is the nature of velocity that comes out of water and abrasive water jet. The water jet machining can be divided into 2 groups. One is water, pure water jet, another one is water jet, this part of the schematic is not relevant. Water comes out, directly machines my job. This is my job, directly machines. All of us will have seen waterfall. Just below the waterfall, there is a portion of the granite on the rock. So, such low pressure water can also erode materials. This water can also machine. However, you cannot machine metallic alloys, you can machine polymers, you can machine leather, and stuff like that. The cutting ability of this water jet can be enhanced by adding abrasives to this particular one. This abrasive mixes with the water, comes out. This can also machine the job. Once again, let us come back to the pure water jet and with stabilizer. Pure water jet means it's commercially pure water. When it comes out, it flares out. When it flares out, because of infringement of air, so as it flares out, cutting ability, the amount of material it can cut, it reduces. So we have to somehow control this. How do we control this flare? We add stabilizers. What are the stabilizers? These stabilizers are nothing but long-term polymers having higher molecular. So once we add those stabilizers to the water jet, flare reduces, it becomes much more focused. We can use the total power of water jet. This is about water jet. Other part of the story is abrasive. There are two different systems of abrasive water jet. One is called entrained abrasive water jet system. Another one is called suspended abrasive water jet system. Out of these two systems, entrained abrasive water jet is much more popular and widely used in the industry. Suspended water jet system is also used. However, its penetration in the manufacturing market is not too high. Entrained water jet basically is composed of three phases: abrasive, water, and air. Suspended is composed of abrasive. Once again, we will go later on into different variants of suspended water jet. Now, what are the general experimental conditions? So, what is this? This is a device. I have not yet named the device, which issues high pressure abrasive water jet. How it is? I will explain briefly. Now there is an orifice which basically transfers pressure energy of the water, kinetic energy, to generate water jet. This orifice is made up of sapphire. Its diameter is around 0.1 to 0.2. In that, the high pressure water is generated. After that, you have a mixing chamber.
पूरा बंद कर निकाल दो.
सर बस वीडियो बंद कर दो.
नहीं बंद नहीं हुई सर वो.
नहीं बंद तो नहीं हुई.
बाकी सब आप कर दो ना. ये मत करना.
मिनिमाइज किया.
वो सर डिस्कनेक्ट हो जाएंगे इसको करोगे ना सर.
अच्छा.
कोई नहीं सर, आप अनाउंस कर दो सर.
Okay. Okay, we stop today here, and we'll again reassemble at 2 o'clock, 2 or 2:15 maximum. Okay, for the next afternoon session. So we have invited one expert lecturer from Punjab Engineering College, Chandigarh. He will be delivering his expert lecture on electrode discharge machining, afternoon at 2:15. It will be about 1.5 hours. Okay.
Okay, sir.
Yes, any queries? Hello? I'm not able to hear. Okay, we'll meet at 2:15 sharp. Okay.
Okay, sir.
Thank you. बस लंच बोल के लिख दीजिए. एक मिनट। आप भी करा जाओ, यू कैन गो फॉर लंच। लॉक करके जाओगे ना इसको कैसे? एक मिनट, थोड़ा सा मैं यहाँ, I'll take 5 minutes. ठीक है, ओके। आप 2 बजे तक आ जाएंगे ना आप भी?
हाँ जी।
ठीक है।
नहीं सर, सेंटर कनेक्ट में टाइम लगेगा सर, ये चलता रहेगा, कॉल चल रही है। आजा कहीं नहीं बेचैन
चाहिए, मेरे को ऐसा लग रहा है ये है। यही है क्या? यही है? यही तो है। इस टाइम यही तो है। अच्छा, अभी सरदार जी आए हैं तो ये सरदार जी आए हैं।
Hello, good afternoon, dear participants. I hope all the nodal centers have been connected right now. RIET? RIET? Are you there, Mr. Avdesh Singh?
Yes, sir.
Okay.
Hello.
Hello.
Yeah, I'm Avdesh Dixit from RIT.
Okay, you are available. All candidates are available right now.
Yes, sir.
Okay. Next center. Then JECRC, Rajasthan.
Yes, sir, we are available. Audible.
Okay, okay. Where is Professor Ram Singh?
Yes, sir.
It is not visible here. Where is he?
No, actually, Professor Ram Singh is busy some event. He is going
Okay,
to
okay.
come.
Okay, fine. No problem. Next, Engineering College, Bikaner, Mr. Dr. Dharmendra Singh. Connected? nahi? Acha. Next, the fourth center, Panipat Institute of Technology, Panipat. कौन है कोऑर्डिनेटर कौन है वहां पे हाँ okay 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 very good afternoon all of you today afternoon session sir किस पे था अच्छा okay today we have expert from Punjab Engineering College Dr. Sarabjit Singh. He has done PhD from Indian Institute of Technology, Roorkee, in advanced machining area. He is having more number of papers in international journal as well as international conferences into his credit. Now, he will be delivering lecture, the expert lecture on conventional and non-conventional machining of metal matrix composites. So, which is his research area, I hope so. So he will be delivering his lecture on conventional and unconventional machining of MMC, that is metal matrix composites. So now I invite Dr. Sarabjit Singh to deliver a lecture on this particular topic. Thank you.
Thank you.
Please.
Thank you, sir. Thank you, Rao, sir. I myself, Dr. Sarabjit Singh from PEC University of Technology. My topic for today's presentation is conventional and unconventional machining of metal matrix composites. So let's start. Okay, welcome all the participants. So the first slide of my presentation is what is the necessity to go for conventional or unconventional machining of metal matrix composites. Specifically here, I'm interested to talk about conventional machining of metal matrix composite. As you check this slide, this slide represents the various utilization of metal matrix composites in the various sectors like in ground transportation, consumer product, industrial, aerospace, and electronic or thermal management system. When you check this slide, you came to know that the major chunk of metal matrix composites are used in ground transportation as well as in the consumer product. What is the basic requirement of a transportation industry or a consumer industry? They are looking for a effective and efficient secondary processing of material. They are not looking for a high-end machining of that material because it causes a increase in the cost of that product. What is basic requirement of my transportation industry and the consumer product is they are looking for a effective and efficient manufacturing process. Right? That's why when we are talking about the aerospace, they are not concerned about the cost of that product. In the case of aerospace, the safety of the passenger or safety of the equipment is more important as compared to the cost, right? So this slide motivate me to work in the field of non-conventional or conventional machining of, particularly conventional machining of metal matrix composites. So this is a survey made by the BCC Research, and it included from 2004 to 2013. Here you check that this blue strips as well as this red strip, this shows that that the metal matrix composites are extensively used in ground as well as in the consumer products. Right, right. When we are talking about the metal matrix composite, we classify the composite into with respect to their matrix as well as with respect to the reinforcement. Now here the broader classification of matrix is metal matrix is with respect to their matrix, that is aluminum based, magnesium based, titanium based, copper based, or superalloy based. Apart from this, the composites are classified with respect to their reinforcement. We call that as a primary reinforcement as well as a secondary reinforcement. So primary reinforcement mean to say when the major chunk of reinforcement is like silicon carbide, it's close to 10 to 15 or 20% of the total volume or the total weight of it, depends. And some secondary reinforcement is used such as graphite to increase the machinability or machining characteristics of that component. That's why we call that as a primary reinforcement and secondary reinforcement. And the composite made with the help of these reinforcement, we call that as a hybrid composite. So we categorize this metal matrix composites as simple composite as well as the hybrid composite. Hybrid composite consists of primary reinforcement and secondary reinforcement. The purpose of secondary reinforcement is to increase the machinability of the dwell component. The various reinforcement we used in these components are silicon carbide, aluminum oxide, boron carbide, so on. Now, when we are talking about the fabrication technique for this metal matrix composite, these fabrication techniques are completely developed. They are basically classified into two categories. One is the solid phase, and second one is the liquid phase. If you check from the diagram, it is classified into two categories: solid phase and liquid phase. In the liquid phase, we have a compo casting, stir casting, liquid metal, squeeze casting, or spray deposition process. In the solid phase, we have a power metallurgy or a diffusion bonding process. Almost close to 70 to 80% of the metal matrix composite, which are aluminum based, are made with the help of a liquid casting route. In that one, persons are using the stir casting as well as the compo casting. Now, what is compo casting? Compo casting is basically in which the casting of the metal or the molten metal as well as the silicon carbide, whatever you mix in that one, is casted in not in the liquid form, but it is casted in the mushy zone. We call that as a composite casting. For example, in the case of aluminium, its melting temperature is close to 650 degrees centigrade. We raise its temperature close to 700 degrees, then we pour silicon carbide. Then we rotate it, stop the furnaces so that we let it cool up to the temperature of 630 or 625, when it becomes a mushy zone, when the liquid is in a mushy zone. Then we pour it. We call that as a compo casting because it is in a mushy zone. It is a semi-solid form. This type of casting we call as a composite casting. So majorly close to 70 to 80% of the composites are made with the help of this liquid casting route. So this is very important. I call this a very important slide. It's basically a comparison of various conventional and non-conventional machining process with respect to the machining of metal matrix composites. So here I made this comparison. This is one of the slides from my book. In this one, the comparison is based upon electro discharge machining. We call that as a EDM. This is a non-conventional machining process. Then electro discharge drilling. It is basically a extension of this EDM process or system concern of the EDM. Then electrochemical machining and ultrasonic machining, and all these are non-conventional machining process, and there is a comparison between non-conventional to the conventional. We call that as a conventional drilling process, right? Now comparison is made with respect to the experimental time, with respect to the material, with respect to burr formation, material removal rate, tool wear rate, accuracy level, and surface roughness, cutting forces and torque, thermal stresses, residual stresses, tool cost, and the power consumption. And here you came to know that when we are talking about the conventional drilling, the experimental time is very, very short. So again, recall the very second slide where we are talking about the need of hour related to the metal matrix composite, where the metal matrix composites are extensively used in the transportation as well as in the consumer product, where the time is a very important factor. You can't afford a component which we are going to machine take a time of close to 20 or 30 or 40 minutes. You require time to drill a hole with that is within a fraction of seconds, right? That is possible with the help of only with the help of a conventional machining. Any of the non-conventional machining process unable to give you the material removal rate as comparable to the conventional machining process. So burr formation is in all the modern machining processes or non-conventional machining processes, burr formation is minimum, but in conventional drilling, burr formation is there. That is a very problematic area when we are talking about the machining of composite. Then material removal rate is in the conventional drilling is very fast as compared to all the processes. Now the tool wear in the case of conventional drilling, conventional machining or drilling is maximum. Why it is maximum? Because there is a direct contact of the abrasive particle with the cutting tool. So as you know, when we are talking about the silicon carbide is the second hardest substance on the earth. When it interact with the solid carbide tool, it simply erode or wear the cutting edge of that tool, whether it is a drilling or it is a machining tool or any other tool, right? So when okay, to overcome this problem, we may go for PCT drills, diamond based bit or PCT based drill bits, but they are very expensive. They increase the overall cost of the production. Okay, we come to this point later on. Then material removal rate is very high, tool wear is maximum. Then accuracy level attained with the help of conventional machining is large as compared to the other machining processes. Surface roughness is again very good as compared to all the processes. Cutting forces, okay. In the case of conventional machining processes, cutting forces are always very large because there is a direct contact between the workpiece as well as the tool. Thermal stresses are very large, residual stresses are large. Okay, the tool cost is again, I already said the tool cost is maximum as compared to the non-conventional machining processes. The power consumption is low. Okay, this table basically represent a comparison between the conventional as well as the non-conventional machining processes related to the metal matrix composite. Apart from this table gives you the scope of work in which you can focus your research area, like burr formation, how to reduce the burr formation in the conventional drilling process. That may be one of your research area, right? So how to decrease the tool wear, that may be one of your area. So this table represent the basic characteristics of this table is it gives you the research potential in the machining of metal matrix composite with respect to non-conventional or conventional machining process. Next is when we are talking about the secondary processing of metal matrix composite. Secondary processing mean to say where we are. What is the difference between primary and secondary? I suppose you are able to recall it. The primary processing is you are going to manufacture a component, that is with the help of a casting or with the help of welding or any other manufacturing process. Secondary processing mean to say when you are actually going to machine it, or you are going to change the properties of that component or that material. We call that as a secondary processing, right? So we categorize this secondary processing into two categories: process to make shape of the product, it called as a machining, drilling, reaming, whatever the process is, we call that is. Then process to alter the properties of the of the product, that is like heat treatment of that product, surface hardening. All these are change in the microstructure. All these are within the domain of secondary processing. So this diagram completely represent the various scope of secondary processing of metal matrix composite. It is within the domain of product shape, product properties. Product shape is with the help of material removal process and with the help of material deformation. And material removal processes included machining, drilling, shaping, milling, etc. And deformation processes including rolling, forging, bending, etc. And final shape of the product, and net product goes to the market for use. Now, product properties: heat treatment of the product, edge hardening, annealing, normalizing, final material property of the product, mechanical property, and change in the microstructure as per your requirement, or as per your requirement related to the tribological aspect of that material. So let's concentrate on the conventional machining of metal matrix composite. So various concern in the conventional drilling of metal matrix composite is tool wear, cutting forces, and surface roughnesses. So as the picture represent, this graph represent the various types of tool bit used, tool material used by the various researcher in the last decade. This data is up to the 2015, I suppose. And here, close to 28% of the researchers use the PCD, that is polycrystalline diamond. Then 19% of the researchers use solid carbide. 19% of the researchers use high-speed steel and coated high-speed steel. 9% uses, other uses 8%, and tungsten carbide close to 17%. Now, the net result of all these tool material is when you are talking about the high-speed steel or coated high-speed steel or tungsten carbide, that is straightway rejected by the researcher, because when you drill up with the help of these tools, it interact with the tool. Then with the solid carbide particle or abrasive particle, the tool is immediately rated, wear out, and its life is in the case of drilling or in the case of machining is negligible when we are talking about the high speed steel or coated high speed steel or tungsten carbide. Okay, some two lives are given by solid carbide and the polycrystalline diamond. If I arrange all these tools in a ascending order, then PCT is at highest level, the second is at solid carbide, and the third one is tungsten carbide, and so on. So here my research work at IIT Roorkee is concentrated only on the solid carbide drill bits, because they are less expensive as compared to the polycrystalline diamond. Their cost is close to 1/20 of the PCDs drill bits. If it is its cost is close to 5,000, then PCD is close to 1 lakh rupees. Okay, in the conventional drilling, the major aspect is cutting wear, tool wear. Then second is cutting forces, as there is a direct contact with the material and the cutting edges. The cutting forces are enormous, in the case of conventional drilling. Okay, the surface roughness is again a major concern in the conventional drilling, because sometimes the loosely bounded silicon carbide particle, they act as a abrasive particle and eroded uh, wear the whole wall surface, because they itself act as a cutting tool. Okay, during my research work, I use various type of drill point geometry to investigate their quality characteristics, to investigate the various quality characteristics. Here, the quality characteristics used are thrust forces, torque, surface roughness, then tool wear, burr formation. All these are output quality characteristics used, and the input parameters are cutting speed, feed, and drill point geometry. I selected these 3 drill point geometry out of 7-8 geometry available to me. The first one is a conventional drill. We call that as a twist drill, right? This one. This one. This one is a conventional drill point geometry. We call this as a Joe drill point geometry, and this is a parabolic drill point geometry, right? So these are selected on the basis of it. I performed some preliminary investigation, and I found that the thrust forces or torque generated in these type of geometries are much lesser than the other geometries. That's why I select these as one of my process parameter for my further investigation, right? Some researcher call this Joe drill point geometry as a step drill point geometry. It consists of a primary step. This is the primary step, and this one is a secondary step, right? And the output quality characteristics here are thrust force. This is a signal generated for thrust force, signal generated for torque, and surface roughness, tool wear, and burr formation. These are the some of the output quality characteristics with respect to this investigation. So this is a schematic diagram for the experimentation work. We have a drill bit, we have a drilling dynamometer. So here as the line diagram represent, this is the dynamometer, and this is the metal matrix composite plate, and it is centrally placed on the dynamometer. And this is the drill point geometry. This is spindle, and the signal from this piezoelectric drilling dynamometer is gone to the charge amplifier, from where it is converted to the analog to digital converter, with the help of analog to digital converter, and converted into the signals, that is in terms of thrust force and torque with respect to time. So this figure represents the actual dynamometer. This is the metal matrix composite plate. It is centrally placed upon the dynamometer. This is a drilling dynamometer workpiece. Dynamometer software with computer. This is the drill point geometry. This is the charge amplifier, which is used to amplify the signal produced with the help of a dynamometer. So these are the signals produced for metal matrix composite. Now here, if you check these signals are erratic in nature. They have ups and downs. It shows that the interaction of drill point geometry with the abrasive particles here, right? And this is a signal for thrust force, and this is a signal for torque. So I perform a number of experiments with respect to different drill point geometry, with various cutting speed, variation in cutting speed, variation in feed, as well as variation in reinforcement size. Here, if you check that with respect to twist drill, with respect to parabolic drill, and with respect to Joe drill, I perform set of experiments on cutting speed. Cutting speed varies from 140, 224, 355, 450 and 560, and the feed varies from 0.03, 0.05, 0.08, 0.12, 0.19 millimeter per revolution. And here the variation in material is also there. It is with respect to the reinforcement size of the abrasive particle. Here the reinforcement size of the abrasive particle is 5 micron, 10 micron, and 15 micron. If you calculate all these parameters here, we have, I suppose we have 5 parameters here. One is drill punch geometry, second is cutting speed, third one is feed, and fourth one is reinforcement. We have 4 parameters, all at a level of feed is at a level of 5, speed is at a level of 5, drill point geometry is at a level of 3, and reinforcement size is at a level of 3. Right? Now it gives you a combination of close to more than 100 experiments. When you are able to plot, if you simply plot those experiments, it gives you a very erratic nature of the result. You are unable to predict what is happening, right? So I place them all these experiments with respect to thrust force mapping. I make some zones. Zones mean to say where the forces are less than 150 newtons. I call that as a weak zone, then intermediate zone 150 to 250, then 250 to 350, then 350 to 450, and 450 to 550, and above 550 newton. That is very high value of thrust forces. I categorize the thrust forces in all this domain with respect to the different feeds, as well as different feeds, cutting speed, as well as the parabolic, various type of drill point geometry. Now, when I came to know that here, under all these parameter, the twist drill point geometry, when the feed is close to 0.119 and reinforcement size is 5, 10, and 15, and the RPM is 140 to 560, all these are red in nature. Okay, all the thrust forces are greater than 550 newton. Now, with respect to the parabolic, there is some decrease in the thrust force, and with respect to the jaw drill point geometry, there is a considerable decrease in the thrust force at the same process parameter. Right? So here the thrust force is within the zone of 450 to 550 newton. In the case of twist drill, it is more than 550. And in the case of parabolic, it is again within the range of 450 to 550, because some are red, some are black, and some are this brown, right? So from this one, I concluded that the drill point geometry has when you kept all the process parameter as a constant, then drill point geometry has a significant effect on the cutting forces. Though you can simply conclude it with the help of this figure here. All these things are dark, and here the cutting forces are less than 450 newton. Right? In the same way, I go for torque mapping. In the same way, I go for the surface roughness mapping. Here, the surface roughness attained is within the zone of 3 to 4, 4 to 5, or micron. All these are in microns. Then 7, 6 to 7, and more than 7. Now, again, you came to know that here the jaw drill point geometry having surface within the range of 4 to 5 as compared to 3 to 4 as compared to parabolic drill point geometry, where the surface roughness is within the zone of 5 to 6, as well as the twist drill point geometry, where the surface roughness is within the zone of 5 to 6. So, from this mapping of thrust force, torque, and reinforcement size, the following conclusions has been made by me. The feed along with drill point geometry are important parameter to consider for analysis the thrust force. The reinforcement size also has a considerable influence on thrust force. the effect of variation in cutting speed on thrust force was not evident from the thrust force mapping. Okay, all these are observation from the thrust force, torque, and uh, surface roughness mapping. Similar to the thrust force, feed, drill point geometry, along with reinforcement size, has considerable effect on torque. Again, the effect of cutting speed was not found significant from torque mapping and was considered as insignificant. From the surface roughness mapping, it was observed that all the precise parameter cutting speed, feed, and drill point geometry and reinforcement size affect the surface roughness of the drilled hole wall in metal matrix composite. Now here, the one very important thing, when very important observation is here, the drill point geometry plays a very significant role when we are talking about the thrust force, when we are talking about the torque, or when we are talking about the surface roughness. So what is the here we have some idea that is qualitative idea. Qualitative idea is drilling geometry is a significant parameter. Drill point geometry is a significant parameter. Now, how to quantify it? So our aim is to quantify it. So we quantify it with the help of some statistical technique. We perform some statistical experiment within the domain of cutting speed, feed, drill point geometry, and reinforcement at level 1, 2, 3 as per the Taguchi methodology. And uh, we find out the various variation of the thrust force with respect to the reinforce speed. This is a speed. It shows that it's almost constant. And with respect to feed, it's a considerable increase in this one. And drill point geometry, there is a decrease in the thrust force, and with respect to the reinforcement size, it is first increasing then decreasing, right? This is some of the observation from. In the same way we have observations for torque as well as observation for the surface roughness, and we quantify it and found that in the case of thrust force, the cutting speed is insignificant. I only present here the graph of cutting this thrust force. The torque and surface roughnesses graphs are not available in this presentation. I simply give the results. Uh, the thrust force, in the case of thrust force, cutting speed is insignificant, and the feed is 79%, drill point geometry 13%, and the contribution of reinforcement size is 7%. And with respect to torque, the contribution of the torque is cutting speed is 6%, feed is 69%, drill point geometry is 15, reinforcement size is 9. Then with respect to surface roughness, cutting speed is 23, feed is 16, drill point geometry is 53, and reinforcement size is 80. Okay, all these percentages basically all these are numbers. So I try to generate some keywords for each and every output quality characteristics, that is thrust force, torque, and surface roughness. The keywords generated are drill point geometry, thrust force में 13%, torque. In the case of torque, drill point geometry is significant, that is close to 15%. Surface roughness highly significant, close to 53%. So what is the meaning of this keyword? Keyword represents that the drill point geometry, that is jaw drill or the step drill, it influences the thrust force, it influences the torque, it influences the surface roughness. You get the best result with the help of this drill point geometry. So it motivated me. What motivated me to carry out the research on particularly on this drill point geometry, that is step drill. So my second phase of experiment starts with the drill point geometry. And one more thing we observe from this one, the burr formation is minimum in the case of step drill point geometry. So up till now, what we did, we performed the inter-drill point geometry. Inter-drill point geometry mean to say when we are comparing the various drill point geometry. Now, in the next phase, we are going for the intra-drill point geometry. Intra-drill point geometry mean to say we have a single drill point geometry. We vary the various cutting characteristics of that. Cutting edges or dimensions of that drill point geometry. Okay, we call that as a intra-drill point geometry investigation. And one more concept we originated from that with the help of variation in the cutting angles of this jaw drill point geometry or step drill point geometry, we are able to decrease the burr formation on the workpiece. So as I said earlier, that the comparison between the non-conventional and conventional machining processes gives you some research challenges. The research challenge in the case of conventional drilling is the burr formation. So what are the various the burr formation causes inappropriate contact angle among grunt carrying members, inappropriate seating of mating surfaces, imprecise assembly of component, additional processing cost for deburring. These are the some of the deficiencies related with the burr formation on the object or on the material in the process of in the conventional drilling of the materials or conventional drilling of the composites. So let's let's check how the burr formation take place in a simple twist drill. Now here you check that in the case of this is a simple twist drill, this is a workpiece and this is the point angle. Okay. If you concentrate on the last portion of the material which is still attached to the workpiece, and the no cutting take place up till now, no cutting take place. We are talking about the end toward the end of the drilling process. Here, if you enlarge this one, the drilling take place, the cutting forces are acting perpendicular to this cutting edge. Okay. Now here it is converted into the two component. One is a horizontal component and second one is the vertical component. Horizontal component and vertical component. I call this component as a Rx and I call this component as a Ry and this component as a component R, which is a cutting force acting on the material. Right now, this vertical component, that component Ry is responsible for the thrust formation, and the horizontal component, that is component Rx, is responsible for twisting of that last flake of the burr or last flake of the material in the form of burr. Okay. Now what happened here? This component rotate this uncut portion of the material and place it somewhere here. We call this portion as a burr. Now this is given. This diagram is given by Co-SL in the year 2003. This is a basic burr formation in the conventional drilling process. Now the point is how to decrease this burr formation. So decrease कैसे करना है? Now you are able to decrease this burr formation if you are able to decrease the horizontal component. Just check. May use the blackboard. Madam, blackboard use कर सकते? Marker नहीं है? Okay, no issues. Let me repeat this. In this twist drill, right? Presentation. Okay. In this drill point geometry, here we are talking about the last flake of the material, uncut material, right? Now here the forces acting on The cutting forces are always acting perpendicular to the material. Here the cutting force is acting something like this. This is the cutting force component. Okay, you can resolve this component into two forces. One is horizontal and second one is vertical. The vertical component is responsible for the thrust force, and horizontal component, what happened, horizontal component try to or rotated the uncut material, and it plays somewhere on the outer face of the workpiece. We call this as a burr formation. This is basically burr. ठीक है, cutting नहीं हुआ, there is no cutting, it is just horizontal component rotated it and it plays somewhere here, right? Now the idea is how to decrease this burr formation. इसको decrease कैसे करना है? So one very simple method is try to decrease the horizontal component. If you decrease this component, horizontal component, the burr formation can be decreased, right? No, this again at a same process parameters, I perform some experiment related to the twist drill and related to the step drill, and I found that in the case of step drill, the thrust force is much less as compared to the twist drill, right? And as well as the burr formation is also negligible in the case of step drill. So this is basically a comparison of thrust force signal for twist drill as well as for the step drill. Okay, again the burr formation in the case of step drill. Okay, we call this as this is a primary cutting edge, and we call these are a secondary cutting edge. Now in our jaw drill, this secondary cutting edge are at some angle. Okay, again they leads to the burr formation, but the burr formation at this point is smaller as compared to the twist drill, because the cutting forces are in this jaw drill point geometry or step drill point geometry, the cutting forces are very much decreased as compared to the twist drill point geometry, right? Now, what I did instead of if you recall this previous figure. Now here the secondary cutting edge has some angle. Here I make the secondary cutting edge that is 180 degree. Instead of some angle 125 or 130 degree, the secondary cutting edge is 180 degree. It is perpendicular, right? I call that as a cutting edge. So here, now what happened? So I make one hypothesis for this burr formation. The burr formation in twist drill is because of cutting forces component acting perpendicular to the drill axis. Okay, we already discussed this thing. Decrease in burr formation may be observed with the step drill point geometry because of decrease in cutting forces as compared to conventional drill point geometry. Okay, then horizontal component of drill force becomes 0 when secondary cutting point angle is 180 degree. अगर मैं इस horizontal component को 0 कर दूं, if by some means I try to make this horizontal component as a 0, then I suppose that there will be no burr formation because no bending will be there, and may cause further decrease in burr formation or burr free holes may be produced. Right? That is my hypothesis, and I work on basis of this hypothesis, and I make a drill point geometry. Here the variation in the process parameters are with respect to the step diameter. The step diameter is 4, 5 and 6, and the point angle is 90 degree, 118 degree and 130 degree, and the secondary cutting edge of drill point geometry is remain constant, that is 180 degree. All these are with the help of all drill bits are of a solid carbide. Now when I perform the experiment, these type of signals, step signals are generated instead of the regular signal. Okay, here if you recall, if you check here, the progress of uh, this drill bit is shown somewhere here. Okay, this represent the point A. At this point, the drill bit is at on the surface of the material. Okay, and this is represent A to B. Please check somewhere over there. Excellent. If you check this A to B, here A to B is when the primary cutting edge is completely in contact with the workpiece material. Then B to C, when the primary cutting edge perform the cutting operation on the material. And C to D represent when primary as well as secondary cutting edge both perform the cutting operation. Then D to E represent when both the primary as well as secondary cutting edge perform the drilling. Then E to F when only secondary cutting edge perform the drilling. Okay, it's E represent the point where the primary cutting edge going to leave the workpiece, and only secondary cutting E to F represent only when there is a steep decrease in the cutting forces, where only the secondary cutting edge perform the drilling. F to G, where when the only secondary cutting edge perform the drilling, then G to H there is a steep decrease in the cutting forces, right? So this represent the flow of you can check the flow of drill point geometry from position A to position H with respect to the various cutting edges, and all these are represented somewhere with the help of the thrust force signal, right? So when you analyze, compare these drill point geometry results, holes made with the help of these drill point geometry, we observe that there is a no burr formation on the exit as well as on the entrance side of the workpiece, as compared to the burr formed on the workpiece with the help of a conventional drill point geometry. Here you check some of this is a very clean hole made with the help of twist drill, but here we have some burr formation, burr formation, burr formation. Here we have some burr formation. Okay, with the help of conventional twist drill point geometry, burr formation is observed. With the help of this modified drill point geometry, the burr formations is reduced to a considerable extent. Okay, some micro burrs may be available over there. They may be shown with the help of microscope or some other magnifying instruments. So when I investigate the chip formation, so two types of chips were observed during the drilling process. One is regular curved shape, V-shaped chips. Okay, and second type of chips are formed with the help of a secondary cutting edge, that they are in a ring type of chip formation, right? So we try to make some analysis how these chips were formed with the help of this secondary cutting edge. So we investigated and came to know that at the end of the drilling process, when only the secondary cutting edge is in action, now what happened? This last flake of the material, it is constrained by the workpiece from this side, constrained by the this cutting tool from this side, constrained by the cutting tool from this side. Okay, this is the extended portion of this one. Okay, this is the workpiece. This is constrained from this side, and uh, vertical forces are acting on the surface. No, no. If you analyze this last flake of the material, it looks like a constraint ring. It looks like a constraint ring. Constraint means to say it is constrained from these two sides, and load is uniformly distributed. Load is acting on the upper side. Okay, as there is a lot of temperature is generated, heat is generated on the surface of this one. Okay, as the base is aluminum base, the coefficient of expansion is very high. No temperature stresses are generated on the last flake of the material. Because of this temperature stresses, the stresses are acting in this direction. Please check this slide. The temperatures these are the thermal stresses. TS represent the thermal stresses. They are acting on the material in this side, right? No, because of these thermal stresses, okay, the material is constrained, completely constrained, right? The forces are acting in this way. Right? The forces are acting in this way, it completely constrained it. That's why the ring type of chip formation is there. Right? Am I able to clear my point?
Sorry, but if you are forming such a sort of a ring, is there is a possibility that it will take off the some portion from the original metal itself, because what you're intended is to make a hole. But it is not a usual gradual forces not coming, because at that time it is perpendicular. That will be perpendicular in the secondary area. So is there any chance that it will be just shear off that due to that force, no? You will just shear off that ring, you will just shear off from the edge. And it may
there may be the chances कि shearing may take place. Shearing may take place. Shearing may take place.
May lead to an underfinished product, or that underfinished mean irreparable loss may happen.
But the thing is कि due to the temperature produced at that zone, it provides the additional stiffness and rigidity to the last flake of the material. Right? Because of the temperature stresses, the material has a tendency to expand. It has a tendency to expand, but you are not going to get it expand because it is constrained from the workpiece side as well as from the tool side. Okay, you are not allowed to allow the material to expand. So what happened here? The stresses will be produced. And it provides the additional stiffness as well as the rigidity to the last flake of the material. And that additional stiffness and rigidity is beneficial for us. It's beneficial. Why it is beneficial? Because
that piece only will be paper.
that piece will be removed from the material.
It will be made as a metal piece.
Yes. That's why we have ring type of chip formation is there. We observe the chips, then we analyze it. Why this type of chips are formed here? Then we concluded it. We go for the literature. We find out some expansion of something related to expansion of shells, expansion of plates. We analyze these are the mechanisms, right? Then we came to know that okay, this may be happening somewhere here. Here it's like basically it's like a hollow plate. Expansion is like a hollow plate. It's a hollow plate.
It cannot expand.
Yes.
In both directions.
Yes.
This direction, this direction.
Yes.
So it will be just. So then there will be a lot of rubbing force there, right?
There will be a lot of
rubbing force will be there in the chip, right? Because it's perpendicular, no?
Yes. Rubbing.
I mean, a lot of friction will be created on that ring surface, right?
Yes,
due to
but what happened in the case of aluminum based material, there is a increase in the temperature at the workpiece. That increase in temperature is very high. It is close to 200 or 250 degrees centigrade. Okay, that increase in temperature is also beneficial because uh, it basically decreases the cutting forces also,
yes.
right?
Because it's a
So
semi-solid
that
state.
increase in temperature is because of the primary cutting edge.
Okay.
So
That
here
increase in
here the
temperature.
how the cutting take place with the primary cutting edge. It heated the material. Okay, when the secondary cutting came into action, no, it has a heated material. It is going to cut a material which is already at a temperature of 200 or 250 degrees centigrade.
Yes.
Right?
Process is a semi-molten stage.
Yes, yes, yes.
In case of aluminum.
Yes.
Because it's
Not semi molten.
Semi-molten,
It's not a semi molten state.
some sort of
Some sort. Okay, you may call it.
semi-solid.
But semi-solid, it started when its temperature is above the lower crystallization temperature of the material, right? But lower crystallization temperature of this aluminum is close to 450. Here, the rise in temperature is not more than 250.
So it won't create any metallurgical changes or nothing like that.
Metallurgical changes will observed when the temperature come to the critical point.
It's not coming to that.
It's not coming up to that.
So my question was that
Still we call that here it's a cold working.
it's a cold.
It's a cold working. That I suppose it's a more appropriate and right word.
In the conventional drill, it's a cold working process. But here it may come to the question was whether it may come to the hot working process.
Yes. Definitely. Okay, these are some SEM images generated from conventional drilling. Here you can see some of the loosely bounded SiC particles on the surface, and as you check, this is a groove formed by the SiC particle, which increases the basic surface roughness of that whole wall surface. Okay, then subsurface damage. Okay, these are the surfaces damages by this one. Then it's not in the case of metal matrix composites, it's not like that key SiC particle always increases the surface roughness of that whole wall surface. Sometimes they act as a burnishing and honing, they produce some burnishing and honing effect. Okay, the SiC particle they itself act as a as a cutting tool, and they may start rubbing with the whole wall surface. Sometimes they generate a groove. Sometimes they act as a burnishing, and they produce some burnishing and honing effect. It depends upon the reinforcement size of the material, right? If the reinforcement size is very large, it's close to 50 or 60 micron, then it is going to produce a groove on the surface. If its size is very small, close to 5 or 10 micron, then it may be going to produce some burnishing or honing effect on the surface. Okay, some burnishing and honing effects were observed by the SiC particle on these surfaces. Okay, here it is surface roughness is 4.79. Here the surface roughness is 3.79. Okay, apart from this, our second motive is here I skipped some of the slides, which shows the results of effect of process parameters on the output quality characteristic. I skip all this in second phase of experiment. Now, in the third phase of experiment, we finalized some parameters related to the jaw drill point geometry. Okay, this will be the parameter of jaw drill or step drill point geometry, which we are going to investigate in the third phase of experiment. in the third phase of experiment, what we did, we developed a process which further increases the surface finish of the drilled hole wall. So basically, it is a online process. We are increasing the surface finish during the process. It's not after the drilling process operation like a abrasive flow machining. It is online drilling process, right? So here we develop a setup. We call this setup as a abrasive assisted drilling. If some burr formation is there, if still some burr formation or micro burring is at the second phase of experiment with the help of step drill geometry, with the help of this process, we are able to reduce it or minimize it. Now, what happened here? As you check this one, this is the drill point geometry. Yeah, this is the drill point geometry. This is a drill point geometry. These are the magnets. We place some magnets, and these are the SiC particles poured on the surface. Okay. During the rotation process, when the drill is rotating at certain RPM, the drill carries the abrasive particles. Now here the cutting is because of the cutting action of the cutting edges, and these abrasive particles are entrapped in the fluid of the drill bit, and that fluid provided them a centrifugal force, and the free particles are impinges on the surface of the hole wall. Right, during the rotation process, centrifugal force is imparted, and because of this centrifugal forces, the silicon carbide particles are impinges on the whole surface, which further increases their surface finish. Apart from this, some pulling action is generated with the help of placement of some magnets. Okay, I place some magnet somewhere here. Now this magnet act as a they try to pull the magnet SiC particle toward them. Right, we magnetize this SiC particle. Okay, they try to pull the magnetic particle. Okay, the various forces acting on this one is forces because of the centrifugal action. One is downward force, that is due to the gravity. Second is centrifugal force. In नीचे भी ऐसे they are coming downward and they are rotating also, and some magnetic pull is there because of the magnetic flux, electromagnetic flux generated over here. So this process further increases the surface finish or surface roughness of the drilled hole wall surface. That is one of the setup we designed at IIT Roorkee.
Will that particles may come out through the flute?
Yes, the property of that fluid is it imparted the centrifugal force to the SiC particle. They are moving in this radial direction as well as downward direction. ऐसे भी जा रहे हैं, नीचे जा रहे हैं. It's because of gravity. In this direction, it is because of the centrifugal force. So this process started after the cutting operation, when hole is already drilled. We let this process go for some time, or for 20 or 30 seconds, not more than that.
But then you have to redesign the flute also, right?
Huh?
You have to redesign the flute also, because in the conventional drilling process, particles will climb up through that flute. In the conventional process, the chips will be climbing up through that flute, right? So if your intention is that you have to carry the whole material downwards.
These particles are basically in a slurry form. It is a water-based slurry or oil-based slurry, in which you have some concentration of the particle, maybe 10 to 15%. It is not a purely a particles. It's a slurry form. We just pour the slurry like like a coolant.
You're just pouring.
You're pouring it. It's pouring it. Right?
But is there any chance that this slurry may be coming up through the conventional, in the conventional drill, if you have to putting some slurry or some chips to this, it will just climb up, in the conventional drilling process. Because due to the particular shape of that fruit.
Okay.
Will it happen here also?
If it is coming upward, then it is again advantageous to us because it is more interacting with the surface, whole wall surface. Because of it's just like a coolant. What I told you, it's just like a coolant. Coolant may you make some additive particle, that is SiC particles in the coolant and pour it. Okay, if it is coming in upward direction, it means it has a more interaction with the whole wall surface. Then it's again advantageous to us. So it is basically, it depends on the time. It's close to 10, 20 second, 30 second, 40 second. Within that one, we are able to very good results. Although it may damage the this cutting tool also. This process is not so simple. It damages the cutting tool also. Yes. Okay. Next is some unconventional machining processes for composite materials. In this one, we discuss this ultrasonic machining. These are also from some figures from my book. Here you have tool holder studies there, converter, ultrasonic transducer is there, and it is basically a mechanical process in which the abrasive particles are impinges on the surface of the material and rotate it, and you get the cavity of the surface, desired surface. Here, this tool is just replicate of the images, replicate of the workpiece you required, right? I suppose this is a very simple process, ultrasonic machining. Then we have electric discharge machining, right? Here the EDM, we call that as the EDM. I would like to concentrate more on electro discharge drilling. Okay, let's concentrate more on this. Basically, this setup is developed by one of the research scholar, that is Abhishek Singh at IIT Roorkee. So he used the conventional EDM process. So he makes some arrangement, something like this. So this is he remove the conventional tool from this one. Okay, then place some motor here, and here this is the cutting tool, right? So what happened here in the electro discharge drilling, the simple EDM process is there, electric discharge is there, as well as the electrode is revolving. It's rotating. Sorry, the electrode is rotating as well as discharge is produced over it. Okay, we call this as a electro discharge drilling. This is the setup available at IIT Roorkee. Okay, from this, after this, we have one more process that we developed at PEC University of Technology, that is electrochemical discharge machining process. It is basically a combination of electric discharge machining, EDM, and ECM process, electrical charge machining. And what are the properties of this EDM and ECM processes are? They are used for the conductive material, but you can use this ECDM process for the non-conductive or for the composite material, such as metal matrix as well as polymer matrix composite. आप दोनों के लिए इसको यूज कर सकते हो. So This is basically a combination of EDM as well as the ECM process, and suitable for hard and brittle electrically non-conductive material. Material removal rate due to thermal heating, melting, and chemical etching of the workpiece. Okay. So this is the schematic diagram. I will show you the real diagram of this figure. Okay. Okay, now you just check here. This spark is generated. Here, this spark is generated because of ECDM process. So this is the ECDM machine. Here, the spark is generated. Here, and here the workpiece is polymer matrix composite (PMCs). Now, how we make the PMCs? That is given somewhere in the slides. Okay, fabrication of hybrid PMCs, polymer matrix composites. Okay. Okay, these are the fabricated composite. Why we call this as a hybrid? Because in this one we use this glass fiber as well as the silicon carbide. We have some layers of silicon carbide, then we place some glass fiber, then we place some araldite over here, matrix epoxy is there, right? And we make a stacking of all these things and make this composite. Okay, these are the some SEM images or hole drilled, micro hole drilled by ECDM processes. These are the SEM images which shows the ECDM processes. Okay, these are the some of my papers, research publications. These are some of research publications. Thanks a lot. Any question, please? Any questions, please? Quick question. Any questions, please?
देखा मैंने कैमरा भी घुमा दिया, एक ही बंदा बैठा है, बाकी सब
कौन मैं?
नहीं बाहर से आएगा करके। अब चला भी था सरदार जी। हाँ?
नहीं वो बोल वहीं से रिकॉर्ड होगा म्यूट को करने का, क्योंकि अभी तो चल रहा है ना किसी का।
If you don't have any query, then we call it a day and we'll reassemble tomorrow again at 10 o'clock. Five college, so you can write down your query. You're not audible. Five college. So you can chat box.
Hello.
Yes, sir.
So, can I have the mail ID for Dr. Sarabjit Singh so that I can write some query to him?
Yes, definitely.
सर आप लिख दीजिए वहाँ पे कोई वर्ड मेरा मेल आईडी पे डिस्प्ले कर
It's Sarab, SARB Sarab. इसमें लिखा नहीं रहेगा अभी, ऑनलाइन लिखना होगा। SARB Sarab 1234 @gmail.com.
Pardon, sir. It's not clear actually.
SARB1234 @gmail.com, sir. You can
SARG
SARB, sir, you can check your chat box.
SARB 1234 @ Thank you, ma'am. Thank you.
Okay. Okay, sir, thank you.